The familiar twinkling stars that dot the night sky are merely the tip of the cosmic iceberg. Beneath the veil of the visible universe lies a realm of mystery and intrigue, a hidden domain populated by celestial wonders that have the power to transform our very understanding of existence.
Thank you so much for watching my videos. Please subscribe to my channel. Thank you.
From the dense, obscuring clouds of dust that conceal the birth of new worlds to the rapidly spinning, ultra-dense remnants of dead stars, the cosmos is teeming with phenomena that defy our conventional notions of space and time. And yet, despite the awe-inspiring grandeur of these cosmic marvels, there exists a class of celestial objects that have long been overlooked, their secrets hidden in plain sight. These are the ancient, metal-poor stars, the primordial relics of the universe's earliest days, forged in the crucible of the Big Bang and honed by the steady march of cosmic time. Containing only the lightest elements, these stellar bodies offer a unique and invaluable window into the formative years of the cosmos, a glimpse into the distant past that has the power to rewrite our understanding of the fundamental forces that have guided the evolution of the universe. But the ancient metal-poor stars are just the beginning. Beneath the veil of the familiar night sky, a tapestry of cosmic wonders awaits, each one a testament to the boundless complexity and beauty of the universe we inhabit. From the search for extraterrestrial intelligence to the unexpected discoveries of exoplanet research, the mysteries of space are vast, and the potential for transformative insights is truly limitless. Join us as we delve into the hidden realms of the cosmos, uncovering the secrets and surprises that lurk beyond the boundaries of our current understanding. Through the exploration of these little-known facts about space, we will uncover a universe of wonder and possibility, one that promises to challenge our most deeply held assumptions about the nature of existence itself. At the heart of this cosmic tapestry of mysteries lies the ancient metal-poor stars, the primordial stellar bodies that represent some of the oldest known objects in the universe. Forged in the immediate aftermath of the Big Bang, these celestial relics offer a unique and invaluable window into the formative years of the cosmos, a glimpse into the distant past that has the power to transform our understanding of the fundamental processes that have guided the evolution of existence. Unlike the bright, young stars that populate the modern universe, these ancient, metal-poor stellar bodies are inherently faint and difficult to detect, their light often obscured by the vast distances and dense interstellar media that separate them from our vantage point on Earth. And yet, despite the formidable challenges that stand in the way of their observation, a small but growing number of these primordial stars have been identified, each one a testament to the remarkable progress of modern astrophysics and the relentless human drive to unlock the deepest secrets of the cosmos. By studying the unique chemical signatures and physical properties of these ancient metal-poor stars, scientists have gained invaluable insights into the fundamental processes that shaped the early universe, from the formation of the first galaxies to the cycle of stellar birth, evolution, and death that has defined the cosmic narrative. And as the search for these celestial relics continues, the potential for unlocking even greater mysteries about the origins and evolution of the cosmos only grows more tantalizing. So join us as we embark on a journey through the hidden realms of the universe, exploring the little-known facts and surprising discoveries that lie beyond the familiar celestial landmarks. From the dense, obscuring clouds that conceal the birth of new worlds to the rapidly spinning, ultra-dense remnants of dead stars, the cosmos is a tapestry of wonders waiting to be unraveled. And at the heart of this grand cosmic drama lie the ancient metal-poor stars, the echoes of the first light that have the power to illuminate the very dawn of existence. As we gaze up at the night sky, the stars that twinkle and shine above us seem to be eternal, unchanging beacons that have illuminated the heavens for untold generations. And yet, the reality is that the stars we observe our diverse and ever-evolving population, each one a testament to the remarkable history of the universe and the cosmic processes that have shaped its intricate tapestry. Among this vast array of stellar bodies, there exists a small but intriguing subset that holds the key to unlocking the mysteries of the early universe, the ancient metal-poor stars that represent some of the oldest and most primordial objects in the cosmos. These celestial relics, forged in the wake of the Big Bang and honed by the steady march of cosmic time, offer us a unique and invaluable window into the formative years of the universe, a glimpse into the distant past that has the power to transform our understanding of the cosmos and the forces that have guided its evolution. To study these ancient metal-poor stars is to embark on a journey through the annals of cosmic history, to peel back the layers of time and space, and to confront the very origins of the universe itself. It is a quest that has captivated the minds of astronomers and astrophysicists for generations as they strive to unravel the secrets of these enigmatic stellar bodies and to unlock the clues they hold about the fundamental processes that shaped the early cosmos. The story of the oldest stars in the universe begins in the immediate aftermath of the Big Bang, that cataclysmic event that gave birth to the cosmos and set in motion the grand cosmic drama that has unfolded over the course of billions of years. In those first fleeting moments after the universe came into being, the fundamental constituents of matter, the protons, neutrons, and electrons that would eventually form the building blocks of the visible universe, were forged in the intense heat and density of the primordial universe. As the universe continued to expand and cool, these elementary particles began to coalesce, forming the first atoms of hydrogen and helium, the lightest and most abundant elements in the cosmos. It was these simple primordial elements that would serve as the raw materials for the formation of the very first stars, the progenitors of the ancient metal-poor stellar populations that we observe in the present-day universe. These first-generation stars, known as population IE stars, were unlike anything we see in the modern cosmos. Composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements, these stellar bodies were the products of a universe that had not yet been enriched by the nuclear forges of more advanced stellar generations. They were the pure and unadulterated offspring of the Big Bang, untainted by the cosmic cycle of star birth, evolution, and death that would come to define the subsequent history of the universe. And yet, despite their simplicity and primordial nature, these population IE stars were not merely passive conduits for the cosmic materials that had been forged in the aftermath of the Big Bang. Rather, they played a crucial role in the early evolution of the universe, serving as the first engines of structure formation and the harbingers of the complex, diverse cosmos we observe today. As these ancient metal-poor stars ignited and began to shine, their powerful gravitational fields attracted and coalesced the surrounding clouds of hydrogen and helium, gradually giving rise to the first galaxies, galaxy clusters, and other large-scale cosmic structures. And as these massive, short-lived stars reached the end of their lives, they exploded in spectacular supernovae, ejecting the heavier elements they had forged through the process of nuclear fusion back into the surrounding medium. It was this process of stellar death and rebirth, the constant recycling of matter and energy that has defined the cosmic narrative, that would ultimately lead to the enrichment of the universe with the heavier elements necessary for the formation of more complex structures, including the planets, moons, and even the organic molecules that are the building blocks of life. Despite the crucial role that these ancient metal-poor stars played in the early history of the universe, they remain one of the most elusive and challenging celestial objects for astronomers to detect and study. Unlike the bright, young stars that populate the modern cosmos, these primordial stellar bodies are inherently faint and difficult to observe, their light often obscured by the vast distances and dense interstellar media that separate them from our vantage point on Earth. One of the primary challenges in detecting these ancient stars lies in their intrinsic properties, because they are composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements like carbon, oxygen, and iron. These stars shine with a relatively low luminosity, emitting far less radiation than their more metal-rich counterparts. This makes them incredibly difficult to spot, even with the most powerful telescopes and instruments. Moreover, the vast distances that separate these primordial stars from the Milky Way galaxy, where most of our observational efforts are focused, further compound the challenge of detection. Many of the oldest known stars in the universe are believed to reside in the outermost reaches of the cosmic web, in the faint, diffuse halos that surround the larger, more prominent galaxies. Detecting their faint, flickering light against the endless expanse of the night sky is akin to finding a needle in a cosmic haystack. And yet, despite these formidable obstacles, astronomers have developed increasingly sophisticated techniques and technologies that have allowed them to uncover a small but growing number of these ancient metal-poor stars. From the use of high-resolution spectroscopy to identify the unique chemical signatures of these primordial stellar bodies, to the deployment of state-of-the-art telescopes and detectors capable of capturing their elusive light, the quest to find and study the oldest stars in the universe has become a crucial frontier in modern astrophysics. As these efforts have progressed, the number of confirmed ancient metal-poor stars has steadily increased, providing astronomers with an ever-growing dataset to explore the properties and characteristics of these cosmic relics. And with each new discovery, our understanding of the early universe and the processes that shaped its evolution has been transformed, as these ancient stars continue to reveal the secrets of the cosmos' formative years. One of the most remarkable and revealing aspects of the ancient metal-poor stars that have been discovered is the unique chemical signatures they bear, a testament to the primordial conditions in which they were forged and the fundamental processes that have governed the evolution of the universe. Because these stellar bodies are composed almost entirely of the lightest elements, hydrogen and helium, their spectra, the patterns of light they emit, are markedly different from the stars we observe in the modern cosmos. Devoid of the heavier elements like carbon, oxygen, and iron that are the products of stellar nucleosynthesis and the explosive death of more advanced stellar generations, the ancient metal-poor stars exhibit a remarkably pure and uncontaminated chemical profile. This lack of heavy elements, or metals as they are known in the parlance of astronomy, is a defining characteristic of these primordial stellar bodies, and it provides a crucial window into the early history of the universe. By analyzing the precise composition of these ancient stars, astronomers can gain invaluable insights into the conditions that prevailed in the immediate aftermath of the Big Bang, when the first generation of stars began to form and the universe was still in its infancy. For example, the relative abundance of certain elements, such as carbon, oxygen, and magnesium, can provide clues about the specific nuclear processes that were taking place within the cores of these primordial stars. And by studying the patterns of absorption and emission lines in their spectra, scientists can gain a better understanding of the temperatures, densities, and other physical properties that defined the environments in which these ancient stellar bodies were born and evolved. Moreover, the chemical signatures of the oldest known stars can also reveal important information about the larger-scale structure and dynamics of the early universe. The distribution and properties of these metal-poor stars, for instance, can shed light on the formation and evolution of the first galaxies, as well as the processes of matter and energy flow that have shaped the cosmic landscape over billions of years. Indeed, the study of the chemical compositions of ancient metal-poor stars has become a crucial tool in the arsenal of modern astrophysicists, as they strive to reconstruct the intricate tapestry of the early universe and to unravel the fundamental forces that have guided its transformation over cosmic timescales. By peering into the spectra of these primordial stellar bodies, scientists are able to glimpse the very building blocks of existence, and to gain a deeper understanding of the origins and evolution of the cosmos we inhabit. As astronomers have continued to push the boundaries of their observational capabilities and to develop increasingly sophisticated techniques for detecting and studying the ancient metal-poor stars in the universe, a small but growing number of these celestial relics have been identified and confirmed. Among the oldest known stars in the cosmos is a remarkable object known as SMSS J031,000, 336 to 670,839.3, a star located in the halo of our own Milky Way galaxy that is believed to have formed just a few 100 million years after the Big Bang. This ancient stellar body, which is estimated to be over 13 billion years old, is remarkable not only for its extreme age, but also for its remarkably pure and primordial chemical composition. Analysis of the spectrum of SMSS J031 has revealed that it contains virtually no elements heavier than hydrogen and helium, with only the barest traces of carbon, oxygen, and other heavier elements. This makes it one of the most metal-poor stars ever discovered, a true relic of the earliest days of the universe that provides a window into the conditions that prevailed in the immediate aftermath of the Big Bang. Another example of an ancient metal-poor star is SDS SJ102, a celestial body located in the Milky Way's halo that is estimated to be over 13.5 billion years old. Like SMSS J031, this star is remarkable for its purity, with an extremely low abundance of elements heavier than hydrogen and helium. Its discovery has provided further evidence of the existence of these primordial stellar relics and has helped to shed light on the processes that shaped the early universe. In addition to these individual stars, astronomers have also identified a number of stellar systems and globular clusters that are believed to harbor some of the oldest known stars in the cosmos. One such example is the Seg-1 dwarf galaxy, a small faint satellite of the Milky Way that is thought to contain a population of ancient metal-poor stars that formed just a few 100 million years after the Big Bang. The discovery and study of these ancient metal-poor stars have proven to be invaluable in our efforts to reconstruct the history of the early universe. By analyzing the chemical compositions and physical properties of these celestial relics, scientists have been able to gain unprecedented insights into the fundamental processes that shaped the cosmos in its earliest stages, from the formation of the first galaxies to the cycle of stellar birth, evolution, and death that has defined the cosmic narrative. Moreover, the continued search for and study of these primordial stellar bodies has become a crucial frontier in modern astrophysics, as scientists strive to push the boundaries of our understanding and to unlock the deepest mysteries of the universe's origins. With each new discovery, the picture of the early cosmos becomes clearer, and the potential for unlocking the secrets of the fundamental forces that have guided the evolution of existence itself grows ever more tantalizing. As astronomers have continued to uncover and study the ancient metal-poor stars that represent some of the oldest known objects in the universe, the insights they have gained have been truly transformative, shedding new light on the fundamental processes that have shaped the cosmos and the intricate dance of matter, energy, and the fundamental forces that have defined the cosmic narrative. One of the most significant insights that has emerged from the study of these primordial stellar bodies is the crucial role they played in the formation and early evolution of the first galaxies. By acting as the gravitational beacons that drew in and coalesced the surrounding clouds of hydrogen and helium, these ancient stars were instrumental in the birth of the earliest galactic structures, setting the stage for the subsequent enrichment of the universe with heavier elements and the emergence of the complex, diverse cosmic landscape we observe today. Moreover, the chemical signatures of these ancient metal-poor stars have provided invaluable clues about the specific nuclear processes that were taking place within the cores of these primordial stellar bodies, as well as the broader physical conditions that prevailed in the early universe. By analyzing the relative abundances of various elements and the patterns of absorption and emission lines in their spectra, scientists have been able to gain unprecedented insights into the temperatures, densities, and other environmental factors that defined the environments in which the first generation of stars were born and evolved. Perhaps most significantly, the study of ancient metal-poor stars has shed new light on the fundamental forces that have guided the evolution of the cosmos, from the initial conditions that prevailed in the wake of the Big Bang to the ongoing processes of stellar birth, evolution, and death that have shaped the universe over the course of billions of years. By confronting the properties and behaviors of these primordial stellar bodies, scientists have been forced to re-evaluate and refine their theories about the nature of gravity, the dynamics of matter and energy, and the underlying principles that govern the structure and evolution of the universe. Indeed, the insights gained from the study of ancient metal-poor stars have been so profound and transformative that they have the potential to rewrite our very understanding of the cosmos and our place within it. As these celestial relics continue to reveal their secrets, we may be forced to confront the limitations of our current models and theories, and to seek out new frameworks and paradigms that can better explain the fundamental nature of existence itself. And as we continue to push the boundaries of our knowledge and to uncover ever more of these ancient metal-poor stars, the potential for unlocking even greater insights into the early universe and the processes that have shaped its evolution only grows more tantalizing. For these primordial stellar bodies, forged in the crucible of the Big Bang and honed by the relentless march of cosmic time, hold the keys to unlocking the deepest mysteries of the cosmos and to revealing the true nature of the universe we call home. In the vast, boundless tapestry of the cosmos, the familiar stars and galaxies that populate the night sky represent only a small fraction of the true grandeur and complexity of the universe we inhabit. Beyond the luminous celestial bodies that captivate the human imagination lie the dark, obscuring regions that have long held the secrets of the cosmos, veiling the distant wonders that lie beyond our direct observation. These enigmatic entities, known as dark nebulae, are vast, billowing clouds of dust and gas that stretch out across the interstellar medium, blocking the light from the stars and galaxies that lie beyond their shrouded boundaries. Unlike the vibrant, glowing nebulae that are illuminated by the energy of nearby stars, these dark, opaque structures appear as somber, forbidding silhouettes against the starry backdrop, their true nature and significance often overlooked in favor of their more visually spectacular counterparts. And yet, despite their humble and often overlooked status, the dark nebulae that permeate the universe hold a wealth of secrets and insights that have the power to transform our understanding of the cosmic landscape. For these dense, obscuring clouds are not merely passive obstructions, but rather dynamic entities that play a crucial role in the formation and evolution of the very structures that define the universe we observe. From the birth of new stars to the formation of complex organic molecules, the dark nebulae that dot the cosmic canvas are the unseen laboratories where the fundamental processes that shape the cosmos unfold. And by delving into the mysteries of these enigmatic structures, scientists have the opportunity to unlock the deepest secrets of the universe and to uncover the forces that have guided the grand cosmic drama since the very beginning of time. At their core, dark nebulae are vast, sprawling clouds of dust and gas that are found throughout the interstellar medium, the tenuous but ubiquitous material that fills the space between the stars. Unlike the brightly illuminated nebulae that are energized by the intense radiation of nearby stellar bodies, these dark, obscuring structures are composed of relatively cool and dense material that is opaque to the passage of light, effectively blocking the view of the celestial objects that lie beyond their boundaries. The primary constituents of dark nebulae are simple, lightweight molecules, primarily hydrogen and helium, with trace amounts of heavier elements like carbon, oxygen, and nitrogen. These molecules are often in a state of low ionization, meaning that their electrons are not stripped away by the intense radiation of nearby stars, allowing them to remain in a neutral, non-excited state that renders them dark and opaque. In addition to these simple molecular compounds, dark nebulae also contain significant quantities of microscopic dust grains, tiny solid particles that range in size from a few nanometers to a few microns in diameter. These dust grains, which are composed of a variety of materials including silicates, carbon, and even complex organic compounds, play a crucial role in the structure and properties of the dark nebulae, serving as the sites for the formation of new molecules and the nucleation of larger solid particles. The interplay between the gas and dust within dark nebulae is a complex and dynamic process, shaped by the fundamental forces of nature and the unique conditions that prevail within these obscuring clouds. The gravitational attraction between the particles can cause them to aggregate and coalesce, forming dense clumps and filaments that serve as the seeds for the formation of new stars and planetary systems. Meanwhile, the intense magnetic fields that permeate the interstellar medium can influence the motion and behavior of the charged dust grains, sculpting the intricate swirling structures that are often observed within these cosmic veils. Moreover, the chemical composition and physical properties of dark nebula can vary significantly depending on their location within the larger cosmic landscape. Regions of high stellar activity, for example, may experience more intense heating and ionization, leading to the formation of more diffuse and translucent structures. Conversely, the dense, cold cores of dark nebula can serve as the incubators for the birth of new stars, where the gradual accumulation of material can lead to the formation of dense protostellar cores that will eventually ignite and shine. While the dark nebulae that dot the cosmic canvas may appear to be mere obstacles to our observation of the distant stars and galaxies, these enigmatic structures play a crucial role in the fundamental processes that have shaped the evolution of the universe. For it is within the shrouded confines of these dense, obscuring clouds that the seeds of new stellar and planetary systems are sown, as the interplay of gravity, magnetism, and the flow of matter and energy give rise to the next generation of celestial bodies. At the heart of this process is the remarkable ability of dark nebulae to serve as the nurseries for the formation of new stars. As the dense clumps and filaments within these cosmic clouds gradually accumulate material under the pull of gravity, the pressure and temperature within the core regions can increase to the point where nuclear fusion is ignited, marking the birth of a new stellar object. This process of star formation is a complex and dynamic one, shaped by the delicate balance between the inward pull of gravity and the upward pressure of the gas and dust within the nebula. As the core of the protostellar cloud contracts, the material that surrounds it is swept up and accreted, forming a spinning disk of gas and dust that will eventually give rise to a planetary system. But the role of dark nebulae in the process of star and planet formation extends far beyond the mere gravitational collapse of their constituent materials. For within these dense, obscuring clouds, a wealth of chemical reactions and physical processes unfold, resulting in the formation of complex organic molecules and the seeding of the raw materials that will eventually coalesce into the planets, moons, and other bodies that populate the cosmos. The dust grains that are so abundant within dark nebulae, for example, serve as the sites for the formation of a wide range of molecular compounds, including the building blocks of life as we know it. As these microscopic particles collide and interact within the dense, cool environments of the nebulae, they can facilitate the synthesis of complex organic molecules such as amino acids and even the precursors to simple cellular structures. Moreover, the magnetic fields that permeate the dark nebula can play a crucial role in the early stages of planet formation, as they influence the motion and behavior of the dust and gas within the protoplanetary disks that surround newly formed stars. By shaping the distribution and accumulation of these materials, the magnetic fields can help to determine the size, composition, and even the ultimate habitability of the planets that will eventually emerge from these cosmic nurseries. In this way, the dark nebulae that have long been seen as mere obstacles to our observation of the distant universe are, in fact, vital components of the grand cosmic drama, serving as the engines of creation that have given rise to the rich tapestry of celestial bodies we observe today. And by delving deeper into the mysteries of these enigmatic structures, scientists have the opportunity to uncover the fundamental processes that have guided the evolution of the cosmos, from the earliest moments after the Big Bang to the present day. Despite the vital role that dark nebulae play in the formation and evolution of stars, planets, and the larger cosmic structures, the very nature of these obscuring clouds presents a significant challenge to the efforts of astronomers and astrophysicists to study and understand them. For unlike the vibrant, luminous nebulae that are illuminated by the intense radiation of nearby stellar bodies, the dark, opaque nature of these cosmic clouds renders them largely invisible to our traditional means of observation and detection. One of the primary obstacles in the study of dark nebulae is the fact that they simply do not emit or reflect enough light to be easily observed with conventional telescopes and instruments. The dust and gas that make up these structures are predominantly composed of cool, neutral molecules that are not excited by the surrounding radiation, and as a result, they do not produce the characteristic emission lines or infrared glow that would make them readily detectable. Moreover, the very property that defines dark nebulae, their ability to block and absorb the light from the celestial objects that lie beyond their boundaries, makes them challenging to observe directly. The obscuring effect of these cosmic clouds can effectively conceal the stars, galaxies, and other structures that lie in the distant background, rendering them invisible to our telescopic observations. To overcome these formidable challenges, astronomers have had to develop increasingly sophisticated techniques and technologies that can peer through the veil of dark nebulae and reveal the secrets that lie within. One of the primary methods involves the use of infrared and submillimeter wavelength observations, which can penetrate the dense, dusty structures and provide a glimpse of the physical and chemical processes that are taking place within. By analyzing the faint infrared glow emitted by the dust grains, or the subtle absorption features that are imprinted on the light of background stars, scientists can glean valuable insights into the composition, temperature, and density of the dark nebulae. Additionally, the use of radio telescopes and the detection of molecular emission lines can provide further clues about the chemical makeup and the dynamics of these enigmatic structures. Moreover, the advent of advanced computer modeling and simulations has played a crucial role in the study of dark nebulae, allowing scientists to experiment with different physical and chemical scenarios and to compare the results to the observational data they have gathered. By creating detailed three-dimensional models of these cosmic clouds, researchers can better understand the complex interplay of gravity, magnetism, and the flow of matter and energy that shape their structure and evolution. Despite the challenges that come with studying these obscuring entities, the drive to uncover the secrets of dark nebulae has only grown stronger in recent years. For as our understanding of the fundamental processes that govern the formation and evolution of stars and planets has deepened, the critical importance of these enigmatic structures has become increasingly clear. And with each new insight gleaned from the study of dark nebulae, the potential for transformative discoveries about the nature of the cosmos only grows more tantalizing. As we continue to delve deeper into the mysteries of dark nebulae and uncover the vital roles they play in the grand cosmic drama, it becomes increasingly clear that these obscuring clouds are not merely passive obstacles to our observation of the distant universe. Rather, they are dynamic and integral components of the intricate tapestry that defines the structure and evolution of the cosmos. From the role of dark nebulae as the incubators for the birth of new stars and planetary systems, to their influence on the chemical and physical processes that shape the interstellar medium, these enigmatic structures are woven into the very fabric of the universe. And as we continue to explore the myriad ways in which these cosmic clouds impact the larger landscape of the cosmos, the potential for new and transformative insights only grows more tantalizing. One of the most fascinating aspects of dark nebulae is their ability to serve as the birthplaces of new stellar and planetary systems. By providing the dense, cool environments necessary for the collapse of material under the pull of gravity, these obscuring clouds give rise to the protostellar cores that will eventually ignite and shine as the stars of the future. And as the material within these clouds continues to accrete and coalesce, it forms the spinning disks of gas and dust that will eventually give birth to entire planetary systems, complete with their own complex geological and atmospheric structures. But the influence of dark nebulae extends far beyond the realm of star and planet formation. Within these dense, shrouded clouds, a wealth of complex chemical reactions and physical processes unfold, resulting in the formation of a diverse array of molecular compounds, including the building blocks of life as we know it. By serving as the sites for the synthesis of these organic molecules, dark nebulae play a crucial role in seeding the cosmos with the raw materials that will eventually coalesce into the complex structures we observe today. Moreover, the magnetic fields that permeate the dark nebula can have a profound impact on the larger-scale structure and evolution of the interstellar medium. By shaping the motion and behavior of the dust and gas within these cosmic clouds, the magnetic fields can influence the distribution and accumulation of material, ultimately affecting the formation and growth of larger-scale structures like star clusters and even entire galaxies. In this way, the dark nebulae that have long been seen as mere obstacles to our observation of the cosmos are, in fact, vital and integral components of the grand cosmic tapestry. They are the unseen laboratories where the fundamental processes of creation and transformation unfold, the hidden engines that drive the evolution of the universe, and the emergence of the rich diversity of celestial bodies we observe today. And as we continue to unravel the mysteries of these enigmatic structures, the potential for new and transformative insights only grows more tantalizing. For by delving deeper into the shrouded realms of the dark nebulae, we have the opportunity to unlock the secrets of the cosmos, to glimpse the forces that have guided the grand cosmic drama since the very beginning of time. In the vast, boundless expanse of the universe, the celestial bodies that populate the cosmos come in a wide and diverse array of shapes, sizes, and behaviors. From the familiar stars that dot the night sky to the colossal, enigmatic black holes that lurk at the hearts of galaxies, the universe is teeming with a wealth of extraordinary and often bewildering phenomena. Yet, among this menagerie of cosmic wonders, there exists a class of stellar objects that stands out as particularly strange and captivating: the neutron stars. These incredibly dense and rapidly spinning remnants of once massive stars are true anomalies in the grand cosmic drama, defying our most fundamental notions of the physical world and challenging the very limits of our understanding of the universe. Formed in the cataclysmic explosions of supernovae, neutron stars are the ultra-compact cores that remain after a large star has exhausted its nuclear fuel and shed its outer layers. Compressed to an astonishing degree by the immense gravitational forces at play, these celestial bodies are composed almost entirely of neutrons, packed together in a state of matter so dense that it borders on the unimaginable. And it is this extreme density, coupled with the rapid spin and intense magnetic fields that characterize neutron stars, that gives rise to their truly bizarre and captivating behaviors. From the powerful bursts of radiation that can outshine entire galaxies to the bizarre phenomena of glitches and pulses that defy our current models of stellar behavior, these enigmatic objects have become a focal point for some of the most cutting-edge research in modern astrophysics. As we delve deeper into the mysteries of neutron stars and unravel the secrets of their strange and captivating behaviors, we are confronted not only with the limitations of our scientific knowledge, but also with the profound philosophical and existential implications that arise from the study of these cosmic anomalies. For in the study of neutron stars, we are forced to confront the very boundaries of our understanding of the physical world and to grapple with the possibility that the universe may operate according to principles that transcend our current models and theories. To understand the strange and captivating behaviors of neutron stars, we must first examine the process by which these extraordinary celestial bodies come into being. The story begins with the life and death of massive stars, those colossal suns that shine with a brilliance that can outshine entire galaxies, yet whose lifespans are but a fleeting moment in the grand cosmic narrative. As these massive stars reach the end of their nuclear fuel, they undergo a dramatic and cataclysmic transformation, shedding their outer layers in a spectacular supernova explosion that can release more energy in a matter of seconds than our own Sun will produce over its entire lifetime. It is in the aftermath of these explosive events that the neutron star is born, the ultra-dense core that remains after the star's outer layers have been blasted away. The process by which a neutron star is formed is a remarkable and truly mind-bending phenomenon. As the star's core collapses under the weight of its own gravity, the immense forces at play compress the protons and electrons within the stellar material, fusing them together to form a sea of neutrons. This transformation, which takes place in a matter of seconds, results in an object that is so dense that a single teaspoon of its material would weigh billions of tons on Earth. The sheer scale of this compression is difficult for the human mind to fully comprehend. Imagine taking the entire mass of the Sun and compressing it down to a sphere just 20 kilometers in diameter. That is the extraordinary density of a neutron star. And yet, despite this incredible compression, these stellar remnants are not simply inert balls of exotic matter, but rather dynamic and highly active celestial bodies that exhibit a wealth of strange and captivating behaviors. At the heart of the fascination with neutron stars lies their truly bizarre and often counterintuitive behaviors, which challenge our most fundamental notions of the physical world and push the boundaries of our scientific understanding. One of the most remarkable features of neutron stars is their incredibly rapid rotation, with some spinning hundreds of times per second, faster than a kitchen blender. This rapid spin, which is a consequence of the extreme compression of the star's mass, gives rise to an intense magnetic field that can be millions of times stronger than the Earth's own magnetic field. It is this combination of rapid rotation and intense magnetism that gives rise to some of the most spectacular and enigmatic phenomena associated with neutron stars. As the star rotates, its powerful magnetic field sweeps through the surrounding space, generating intense beams of electromagnetic radiation that can be detected from Earth as pulsating, or pulsed signals. These pulsars, as they are known, are among the most precisely timed objects in the universe, with their pulses occurring with a regularity that rivals the accuracy of the world's best atomic clocks. By studying the properties of these pulses, astronomers have gained invaluable insights into the nature and behavior of neutron stars, and have even used them to make groundbreaking discoveries in fields ranging from general relativity to the nature of matter at extreme densities. But the bizarre behaviors of neutron stars extend far beyond the regular pulsations of the pulsars. Some of these stellar remnants exhibit a phenomenon known as glitches, sudden and unpredictable changes in their rotation rate that defy our understanding of the physics that should govern their behavior. These glitches, which can occur without warning and can cause the star's rotation to speed up or slow down, are a testament to the complex and often unpredictable nature of the processes taking place within the ultra-dense interiors of neutron stars. Moreover, some neutron stars have been observed to exhibit dramatic and seemingly random bursts of high-energy radiation, releasing in a matter of seconds more energy than our Sun would produce over the course of several years. These magnetars, as they are known, are believed to be the product of the extreme magnetic fields that characterize these stellar bodies, with the bursts being triggered by sudden rearrangements or instabilities in the star's magnetic structure. The sheer scale and intensity of the phenomena associated with neutron stars are truly mind-bending, pushing the boundaries of our scientific understanding and challenging our most deeply held assumptions about the nature of the physical world. And as we continue to study these cosmic anomalies, we are sure to uncover even more extraordinary and unexpected behaviors that will force us to rethink our models and theories and to confront the very limits of our knowledge. In the vast, boundless expanse of the universe, the human species has long pondered the tantalizing possibility of not being alone, that somewhere, amid the countless stars and galaxies that populate the cosmic canvas, there may exist other intelligent forms of life, beings with the capacity to shape and influence the very fabric of existence. This enduring question, known as the search for extraterrestrial intelligence, SETI, has captivated the human imagination for generations, driving scientists, philosophers, and science fiction enthusiasts alike to ponder the implications of discovering evidence of intelligent life beyond our own planet. For if such a discovery were to be made, it would undoubtedly transform our understanding of the universe and our place within it, shattering the boundaries of our known reality and opening up a realm of extraordinary possibilities. At its core, the search for extraterrestrial intelligence is a quest to unravel one of the deepest and most profound mysteries of the cosmos, the question of whether life, and in particular intelligent life, is a unique phenomenon confined to the Earth, or whether it is a common occurrence throughout the universe. And as our understanding of the fundamental processes that govern the formation and evolution of planetary systems has grown, the potential for the existence of habitable worlds beyond our own has become increasingly tantalizing. From the discovery of thousands of exoplanets orbiting distant stars to the ongoing exploration of the myriad potential habitats for life within our own solar system, the scientific community has amassed a wealth of evidence suggesting that the conditions necessary for the emergence of life may be far more common than previously thought. And with each new advance in our technological capabilities, the tools and techniques available for the detection of extraterrestrial intelligence have become increasingly sophisticated, opening up new frontiers of exploration and discovery. Yet, despite the profound implications of such a discovery and the relentless efforts of countless researchers and enthusiasts, the search for extraterrestrial intelligence has yet to yield any definitive, widely accepted evidence of intelligent life beyond Earth. And as the decades have passed, the quest to make this transformative discovery has become increasingly complex, with new challenges and obstacles emerging that have forced scientists to rethink and refine their approaches. One of the primary challenges that has confronted the search for extraterrestrial intelligence is the sheer vastness of the universe and the daunting distances that separate the countless stars and galaxies that populate the cosmic canvas. With the nearest stars located light years away from our own solar system, and the likelihood of intelligent life existing on distant worlds, the task of detecting and communicating with potential extraterrestrial civilizations has proven to be an immense and daunting undertaking. Moreover, the very nature of the signals or evidence that scientists are seeking to detect adds an additional layer of complexity to the search. Unlike the visible or radio emissions that are produced by the natural processes of stars and galaxies, the electromagnetic signatures that would be associated with extraterrestrial technology are likely to be exceedingly faint and difficult to distinguish from the background noise of the universe. To overcome these challenges, the SETI community has had to develop increasingly sophisticated and innovative methods of detection and analysis, leveraging the power of modern computing and the growing capabilities of radio telescopes and other observational instruments. From the search for narrowband radio signals that could be the product of advanced technology to the analysis of complex patterns in cosmic data that could indicate the presence of extraterrestrial intelligence, the approaches employed by SETI researchers have become increasingly nuanced and multifaceted. And yet, despite these efforts, the search for extraterrestrial intelligence has remained an endeavor fraught with uncertainty and the potential for disappointment. For even as our technological capabilities have advanced, the vastness of the universe and the inherent difficulties in detecting the potential signatures of alien civilizations have continued to pose formidable challenges, leaving the ultimate question of whether we are alone in the cosmos unresolved. But the search for extraterrestrial intelligence is not merely a scientific quest to uncover new knowledge about the universe and the distribution of life within it. Rather, it is a deeply philosophical and existential undertaking that has the potential to transform our most fundamental conceptions of our place in the cosmos and to challenge the very boundaries of our understanding of the nature of existence itself. For if the discovery of intelligent life beyond Earth were to be made, it would force us to confront a host of profound and unsettling questions about the uniqueness of our own existence, the origins of life, and the true nature of the universe that we inhabit. Are we, the human species, truly alone in our capacity for self-awareness and complex cognition? Or are we merely one among countless civilizations scattered throughout the cosmos, each one grappling with the same questions and mysteries that have captivated humanity for millennia? Moreover, the implications of such a discovery would extend far beyond the realm of science, delving into the very heart of our philosophical and religious beliefs about the nature of existence, the role of intelligent life, and the possibility of a cosmic community of which we are but a small part. The discovery of extraterrestrial intelligence would challenge our most deeply held assumptions about the significance and purpose of human life, and could potentially lead to a profound transformation in our understanding of our place within the grand cosmic narrative. And yet, the search for extraterrestrial intelligence is not merely a quest to uncover the answers to these existential questions. It is also a testament to the boundless human curiosity and the relentless drive to explore the unknown, to push the boundaries of our knowledge, and to confront the deepest mysteries of the universe. For in the pursuit of this extraordinary endeavor, we are not only seeking to unlock the secrets of the cosmos, but also to gain a deeper understanding of our own nature and the true scope of the remarkable universe we call home. As we consider the profound implications and enduring challenges of the search for extraterrestrial intelligence, it is clear that this quest is one that will continue to captivate and inspire humanity for generations to come. For whether or not we ever succeed in detecting unambiguous signs of intelligent life beyond our own planet, the very act of seeking out such evidence has the power to transform our understanding of the universe and our place within it. Indeed, the search for extraterrestrial intelligence is not merely a scientific endeavor, but a deeply philosophical and existential undertaking that has the potential to reshape our most fundamental conceptions of the nature of existence. From the implications of discovering that we are not alone in the cosmos, to the profound questions that would arise about the origins and purpose of intelligent life, the quest to uncover evidence of alien civilizations is one that has the power to challenge the very boundaries of our knowledge and understanding. And yet, despite the daunting challenges that have confronted the SETI community over the decades, the drive to continue this extraordinary exploration has only grown stronger. With each new advance in our technological capabilities and our scientific understanding of the universe, the potential for unlocking the mysteries of extraterrestrial intelligence becomes ever more tantalizing, fueling the relentless pursuit of this transformative discovery. Whether through the development of ever more sensitive radio telescopes and signal processing algorithms, the exploration of potentially habitable worlds within our own solar system, or the continued study of the fundamental processes that govern the formation and evolution of planetary systems, the path forward for the search for extraterrestrial intelligence is one that is paved with both challenges and opportunities. And as we continue to push the boundaries of our knowledge and to confront the deepest mysteries of the cosmos, we may well uncover insights and revelations that have the power to redefine our very conception of the universe and our place within it. For the search for extraterrestrial intelligence is not merely a quest to find evidence of alien life, but a profound exploration of the nature of existence itself, a journey that has the potential to transform our understanding of the remarkable and wondrous universe we call home. For centuries, humanity has gazed up at the night sky, captivated by the endless expanse of celestial bodies that populate the cosmos. And while our understanding of the universe has grown exponentially over the course of generations, the profound question of whether life exists beyond the confines of our own planet has remained a tantalizing mystery, one that has captivated the human imagination and driven countless scientific endeavors. Indeed, the search for habitable worlds beyond Earth has become a crucial frontier in modern astronomy and planetary science, as researchers around the world seek to unravel the secrets of our solar system and the myriad of potentially life-bearing environments that may exist within it. From the icy moons of Jupiter and Saturn to the enigmatic dwarf planets that orbit the distant reaches of our star system, the potential for the emergence of life in these otherworldly realms has become a subject of intense scientific fascination and exploration. But the quest to identify and study these potential havens for extraterrestrial life is no simple task. The conditions necessary for the development and sustenance of even the most primitive forms of life are remarkably specific, requiring a delicate balance of factors such as temperature, atmospheric composition, the availability of liquid water, and the presence of essential chemical building blocks. And as our knowledge of the diverse and often extreme environments that exist throughout the solar system has grown, the challenges involved in identifying and characterizing these potentially habitable worlds have become increasingly complex. Yet, despite these formidable obstacles, the drive to uncover the secrets of life's origins and distribution in the cosmos has only intensified in recent years. With each new discovery and technological advancement, the boundaries of our understanding have been pushed ever further, revealing a solar system teeming with a wealth of unexplored and often unexpected potential habitats for life. One of the most intriguing and actively explored potential habitats for life within our solar system is the icy moon of Europa, which orbits the giant planet Jupiter. Beneath its frozen, cracked surface, Europa is believed to harbor a vast, global ocean of liquid water, kept in a perpetual state of fluidity by the powerful tidal forces exerted by Jupiter's massive gravitational pull. This tantalizing prospect of a subsurface ocean, coupled with the presence of essential chemical compounds and the potential for hydrothermal activity to provide a source of energy, has made Europa a prime target for astrobiological exploration. Indeed, numerous missions have been proposed and are currently in development, each one aimed at unraveling the mysteries of this enigmatic world and determining the viability of its environment for the emergence and sustenance of life. But Europa is not the only moon in our solar system that has captured the attention of scientists searching for habitable realms beyond Earth. The icy, geologically active moons of Saturn, such as Enceladus and Titan, have also emerged as compelling candidates for further exploration, with each world offering a unique and intriguing set of conditions that may be conducive to the development of life. On Enceladus, for example, the presence of geysers that erupt from the moon's southern polar region have provided tantalizing evidence of a subsurface ocean, one that may be enriched with the chemical building blocks necessary for life. And on Titan, the largest moon of Saturn, the combination of a thick, nitrogen-rich atmosphere and the potential for liquid methane on the surface has sparked the imagination of researchers who envision a world where life may have evolved in strikingly different ways than it has on our own planet. Beyond the icy moons of the gas giants, the dwarf planet Ceres, which resides in the asteroid belt between Mars and Jupiter, has also emerged as a potential haven for life. Observations from NASA's Dawn spacecraft have revealed the presence of water ice and organic compounds on the surface of this enigmatic world, hinting at the possibility of a subsurface ocean and the potential for habitable environments. While the search for potentially habitable worlds within our own solar system has continued to captivate the scientific community, Another extraordinary frontier in the quest to uncover the secrets of life in the cosmos has emerged in the form of exoplanet research, the study of the countless planets that orbit distant stars beyond our own Sun. In the decades since the first confirmed detection of an exoplanet in the early 1990s, the pace of discovery has accelerated at a truly remarkable rate, with thousands of these extrasolar worlds now known to exist. And as our observational capabilities and analytical techniques have grown ever more sophisticated, the diversity and complexity of the exoplanet population has become increasingly apparent, challenging our preconceived notions about the nature of planetary systems and the conditions necessary for the emergence of life. From the discovery of super-Earths, rocky worlds that are significantly larger than our own planet, to the identification of hot Jupiters, gas giants that orbit perilously close to their host stars, the exoplanet census has revealed a cosmos teeming with a wealth of unexpected and often bewildering planetary environments. And as researchers have delved deeper into the properties and characteristics of these distant worlds, the potential for the existence of habitable Earth-like planets has become increasingly tantalizing. Indeed, the identification of potentially habitable exoplanets, such as Kepler-186 and Kepler-452b, has captivated the scientific community and the public alike, sparking renewed enthusiasm for the search for extraterrestrial life and the exploration of the cosmic conditions necessary for its emergence. And with the continued development of ever more powerful telescopes and analytical tools, the pace of exoplanet discovery and characterization is only expected to accelerate in the years and decades to come. But the significance of exoplanet research extends far beyond the mere identification of potentially habitable worlds. By studying the diverse array of planetary systems that exist throughout the cosmos, researchers have gained invaluable insights into the fundamental processes that govern the formation and evolution of planets, as well as the complex interplay between these celestial bodies and the stars they orbit. From the role of stellar activity and tidal forces in shaping the properties of exoplanets to the insights gleaned about the early stages of planetary system formation, the study of worlds beyond our own solar system has become a crucial frontier in our understanding of the cosmos and the forces that have shaped the development of the universe we inhabit. As we continue to explore the vast and ever-expanding frontiers of space, it becomes increasingly clear that the universe is a realm of boundless wonder and unexpected discovery. From the enigmatic dark nebulae that shroud the birth of new worlds to the bizarre and captivating behaviors of neutron stars, the cosmos is teeming with a wealth of phenomena that challenge our most deeply held assumptions about the nature of existence. And as our observational capabilities and analytical tools have grown ever more sophisticated, the potential for uncovering new and unexpected cosmic anomalies has only increased, whether it's the sudden, unexplained bursts of energy emitted by certain neutron stars, the mysterious and unexplained signals detected by SETI researchers, or the baffling properties of the dark matter and dark energy that appear to dominate the universe. The cosmos is rife with mysteries that continue to defy our current understanding. Indeed, the study of these cosmic anomalies has become a crucial frontier in modern astrophysics and cosmology, as scientists grapple with the limitations of their knowledge and strive to unravel the fundamental forces and processes that shape the grand tapestry of the universe. And with each new discovery and each unexpected revelation, the potential for transformative insights only grows more tantalizing, promising to rewrite our very conception of the cosmos and our place within it. Whether it's the search for evidence of extraterrestrial intelligence, the quest to uncover the origins and evolution of the solar system's habitable havens, or the ongoing exploration of the bizarre and captivating behaviors of neutron stars, the mysteries of space are a testament to the boundless complexity and beauty of the universe we inhabit. And as we continue to push the boundaries of our knowledge and to confront the unexpected, we are sure to be confronted with profound and unsettling questions about the nature of existence itself. Yet, in the face of these profound mysteries, the human spirit of curiosity and exploration remains undaunted. For it is in the pursuit of the unknown, in the relentless drive to uncover the secrets of the cosmos, that we find the true essence of the scientific endeavor, a quest to understand our place in the grand tapestry of the universe, and to unlock the profound and transformative insights that lie waiting in the shadows of the unknown. In the vast, ever-expanding tapestry of the universe, the celestial bodies and phenomena that captivate our attention are but the tip of the cosmic iceberg. Beneath the familiar stars and galaxies that populate the night sky lies a realm of mystery and intrigue, a domain of the unknown that continues to defy our most sophisticated scientific understanding. From the sudden, inexplicable bursts of energy that emanate from the depths of space to the baffling anomalies that seem to challenge the very foundations of our physical laws, the cosmos is teeming with a wealth of unexplained phenomena that have captured the imagination of scientists and the public alike. And as our observational capabilities and analytical tools have grown ever more sophisticated, the potential for uncovering new and unexpected cosmic mysteries has only increased, pushing the boundaries of our knowledge and forcing us to confront the limitations of our current models and theories. Indeed, the study of these unexplained anomalies and phenomena has become a crucial frontier in modern astrophysics and cosmology, as researchers strive to unravel the deepest secrets of the universe and to unlock the fundamental forces that have guided its evolution. For within these enigmatic events and occurrences lies the potential for transformative insights, the possibility of revealing new and revolutionary principles that could rewrite our very conception of the cosmos and our place within it. Whether it's the search for evidence of exotic particles that could shed light on the nature of dark matter, the investigation of the mysterious fast radio bursts that continue to baffle astronomers, or the ongoing exploration of the bizarre and captivating behaviors of black holes, the quest to confront the cosmic unknown has become a driving force in the scientific community. And as we continue to push the boundaries of our knowledge and to confront the unexpected, the potential for unlocking the most profound secrets of the universe only grows more tantalizing. Among the most dramatic and perplexing of the unexplained phenomena that have captured the attention of astronomers and astrophysicists are the enigmatic events known as gamma-ray bursts. These intense, fleeting flashes of high-energy radiation, which can outshine entire galaxies for a matter of seconds or minutes, have long been a source of fascination and intrigue in the scientific community, as researchers have struggled to unravel the underlying causes and mechanisms that give rise to these cosmic fireworks displays. The discovery of gamma-ray bursts, which was first made in the late 1960s by a network of military satellites designed to detect the signatures of nuclear weapons tests, was a truly revolutionary moment in the field of astrophysics. For these brief, intense bursts of gamma radiation, which can be detected from across the vast expanse of the observable universe, represented a new and entirely unexpected class of cosmic events, one that challenged the prevailing models and theories of the time. In the decades that followed, as astronomers and astrophysicists have continued to study and analyze the properties of gamma-ray bursts, a wealth of new insights and mysteries have emerged. Through the use of sophisticated telescopes and detectors capable of capturing the faint, fleeting emissions associated with these events, researchers have been able to determine that gamma-ray bursts can be broadly classified into two distinct categories: short-duration bursts and long-duration bursts. The short-duration bursts, which typically last for less than 2 seconds, are believed to be the result of the merger of two neutron stars, the ultra-dense, rapidly spinning stellar remnants that are the product of the catastrophic collapse of massive stars. These cataclysmic events, which are thought to release a tremendous amount of energy in the form of gravity waves and high-energy radiation, provide a tantalizing window into the exotic physics that govern the behavior of matter and energy in the most extreme conditions imaginable. In contrast, the long-duration gamma-ray bursts which can last for several minutes or more, are believed to be associated with the dramatic and violent deaths of massive stars. As these colossal suns reach the end of their lives and undergo supernova explosions, the intense gravitational forces at play can give rise to the formation of a black hole, which in turn can power a powerful collimated jet of high-energy particles and radiation that is observed as a gamma-ray burst. And yet, despite the wealth of insights and the remarkable progress that has been made in understanding the underlying causes of these cosmic events, the study of gamma-ray bursts continues to be fraught with mystery and uncertainty. For the sheer scale and intensity of the energy released during these bursts, as well as the speed and unpredictability with which they occur, have made them remarkably challenging to observe and study in detail. Moreover, the potential implications of these enigmatic phenomena extend far beyond the realm of astrophysics, as the study of gamma-ray bursts has the potential to yield transformative insights into the fundamental nature of the universe and the forces that govern its behavior. From the insights that can be gleaned about the physics of neutron stars and black holes to the implications for the origins of heavy elements in the cosmos, the quest to unravel the mysteries of gamma-ray bursts is a pursuit that has the power to rewrite our very conception of the cosmos. Alongside the dramatic and attention-grabbing gamma-ray bursts, another class of unexplained cosmic phenomena has emerged in recent years to captivate the scientific community and the public imagination: the enigmatic fast radio bursts, or FRBs. These fleeting, high-energy pulses of radio waves, which can last for mere milliseconds and originate from unknown locations across the observable universe, have posed a profound challenge to our current understanding of the cosmos. Unlike the gamma-ray bursts, which are thought to be associated with the most extreme and violent events in the universe, the sources and mechanisms behind fast radio bursts have remained stubbornly elusive, defying the efforts of astronomers and astrophysicists to unravel their underlying causes. The first confirmed detection of a fast radio burst was made in the year 2007, when a team of researchers analyzing data from a radio telescope in Australia stumbled upon a brief, intense pulse of radio waves that appeared to originate from beyond our own Milky Way galaxy. In the years that followed, as astronomers have continued to scan the skies with ever more sensitive radio telescopes, the number of known fast radio bursts has grown exponentially, with hundreds of these baffling events now having been detected and catalogued. And yet, despite the wealth of observational data that has been accumulated, the true nature of fast radio bursts remains a profound mystery. Unlike the gamma-ray bursts, which can be linked to the catastrophic events associated with the deaths of massive stars or the mergers of neutron stars, the sources of these radio pulses appear to be far more diverse and unpredictable, spanning a wide range of potential cosmic origins. Some theories have suggested that fast radio bursts could be the product of highly magnetized neutron stars, known as magnetars, which could be generating powerful bursts of radio emission as a result of sudden changes or rearrangements in their intense magnetic fields. Others have proposed that these events could be the result of the interaction between black holes and dense clouds of gas and dust, or even the signatures of advanced extraterrestrial technologies, such as powerful communication or propulsion systems. And as if the fundamental mystery of the origins of fast radio bursts were not enough, these enigmatic events have also presented researchers with a wealth of additional puzzles and conundrums. For example, the fact that many fast radio bursts appear to be one-time, non-repeating events has made it challenging to study them in detail and to pinpoint their precise locations within the cosmos. Moreover, the discovery of a small number of fast radio bursts that do appear to repeat, emitting multiple pulses over the course of days or weeks, has further complicated the efforts to understand their underlying causes, as these recurring events do not fit neatly into the models that have been proposed to explain the more common, one-off bursts. As the study of fast radio bursts has continued to evolve, the potential implications of these enigmatic events have only grown more profound. For if the sources of these baffling pulses of radio waves were to be definitively identified and understood, it could yield transformative insights into the fundamental nature of the universe and the forces that govern its behavior. From the physics of neutron stars and black holes to the possibility of the existence of advanced extraterrestrial civilizations, the quest to unravel the mysteries of fast radio bursts has become a crucial frontier in modern astrophysics and cosmology. While the unexplained phenomena that have captivated the scientific community in recent years have largely been the subject of rigorous, evidence-based research and analysis, one category of cosmic mystery has continued to defy the efforts of both scientists and the general public to unravel its secrets: the enduring enigma of unidentified aerial phenomena, more commonly known as UFOs. For centuries, the sighting of strange, unidentified objects in the skies above has captured the human imagination, sparking speculation and debate about the possible existence of extraterrestrial visitations and the nature of the universe we inhabit. And despite the efforts of numerous government agencies, scientific organizations, and independent researchers to investigate and explain these phenomena, the true origins and nature of unidentified aerial phenomena have remained stubbornly elusive, defying our current understanding of the physical world. At the heart of the fascination with unidentified aerial phenomena is the tantalizing possibility that these baffling sightings could represent evidence of advanced extraterrestrial technology, of civilizations beyond our own that have the capacity to traverse the vast distances of interstellar space. This prospect, which has fueled countless works of science fiction and captivated the public imagination, has driven countless individuals to devote their time and resources to the search for definitive proof of the existence of UFOs and their alleged alien origins. And yet, despite the countless reported sightings and the wealth of photographic and video evidence that has accumulated over the years, the scientific community has largely remained skeptical of the extraterrestrial hypothesis, citing the lack of conclusive verifiable data and the inherent challenges in distinguishing genuine anomalies from more prosaic explanations, such as misidentified natural phenomena or human-made objects. Indeed, the very nature of unidentified aerial phenomena, with their fleeting, often inexplicable appearances and disappearances, has made them notoriously difficult to study and analyze in a rigorous scientific manner. Without the ability to reliably document and reproduce these events under controlled conditions, the quest to unravel the mysteries of UFOs has often been relegated to the realms of speculation and conjecture, fueling a wealth of conspiracy theories and alternative explanations that have further obscured the potential for genuine scientific inquiry. And yet, even as the mainstream scientific community has largely dismissed the possibility of extraterrestrial origins for unidentified aerial phenomena, the enduring fascination with this cosmic enigma has continued to captivate the public imagination. From the countless personal accounts of UFO sightings to the ongoing efforts of independent researchers and enthusiasts to gather and analyze evidence, the quest to uncover the truth about the nature of these mysterious objects has become a deeply personal and compelling endeavor for many. Indeed, the continued existence of unidentified aerial phenomena and the persistent lack of a definitive scientific explanation for their origins has become a testament to the limitations of our current understanding of the universe and the forces that govern its behavior. For if these objects do indeed represent the manifestation of advanced extraterrestrial technologies, their very existence would challenge our most fundamental assumptions about the nature of life, intelligence, and the potential for cosmic exploration and colonization. And as the search for the truth about unidentified aerial phenomena continues, the potential for transformative insights and the confrontation of the unknown only grows more tantalizing. Whether these mysterious objects ultimately prove to have prosaic earthly origins or represent the first concrete evidence of intelligent life beyond our own planet, the quest to unravel their secrets has become a crucial frontier in the ongoing exploration of the mysteries of the cosmos. As we bring our journey through the little-known facts and unexplained phenomena of the universe to a close, it becomes increasingly clear that the cosmos we inhabit is a realm of boundless wonder and perpetual mystery. From the sudden, inexplicable bursts of energy that emanate from the depths of space to the baffling anomalies that seem to challenge the very foundations of our physical laws, the universe is teeming with a wealth of unexplained events and occurrences that continue to defy our current understanding. Yet, in the face of this cosmic unknown, the human spirit of curiosity and exploration remains undaunted. For it is in the pursuit of the mysteries that lie beyond the boundaries of our knowledge that we find the true essence of the scientific endeavor, a quest to unravel the deepest secrets of the universe and to unlock the profound and transformative insights that could rewrite our very conception of the cosmos and our place within it. Whether it's the search for the origins of gamma-ray bursts and fast radio bursts, the investigation of the bizarre and captivating behaviors of black holes and neutron stars, or the ongoing efforts to uncover the truth about unidentified aerial phenomena, the study of these unexplained anomalies has become a crucial frontier in modern astrophysics and cosmology. And as we continue to push the boundaries of our observational capabilities and analytical tools, the potential for uncovering new and unexpected cosmic mysteries only grows more tantalizing. Indeed, the embrace of the cosmic unknown, the willingness to confront the limitations of our knowledge, and to seek out the transformative insights that lie beyond the edges of our understanding, is a hallmark of the scientific spirit that has driven human progress for centuries. It is this relentless pursuit of the unknown, this drive to explore the furthest reaches of the universe and to uncover the fundamental forces that govern its behavior, that has transformed our conception of the world and our place within it time and time again. And as we look to the future, it is clear that the mysteries of the cosmos will continue to captivate and inspire us, propelling us ever deeper into the unknown and challenging us to confront the most profound questions about the nature of existence itself. For in the study of these unexplained phenomena, we are not merely seeking to uncover new facts and insights, but to unlock the very secrets of the universe and to gain a deeper understanding of the boundless complexity and beauty that define the world we inhabit. So let us embrace the cosmic unknown and let it fuel our curiosity, our creativity, and our relentless drive to explore the furthest reaches of the universe. For in doing so, we may well uncover the transformative insights that could rewrite the very fabric of our reality and unlock the profound and awe-inspiring truths that lie at the heart of the grand cosmic drama. Have you ever wondered how the universe as we know it came into existence? What was the spark that ignited the grand cosmic drama we are all a part of? The answer to these profound questions lies in a remarkable scientific theory known as the Big Bang. Imagine, if you will, the entire known universe, every galaxy, every star, every planet, and every particle of matter and energy compressed into a space so infinitely small that it defies the limits of our comprehension. This inconceivably dense and hot state was the starting point of our universe, existing in a state of unimaginable compression and tension, just moments before the remarkable event we call the Big Bang. It was a moment of pure potential, a singularity in the fabric of space and time, where the laws of physics as we understand them break down and the very nature of reality becomes a mystery. And then, in a cataclysmic explosion of unparalleled power, this primordial state was shattered and the universe as we know it was born. The Big Bang theory, first proposed by the Belgian priest and physicist Georges Lemaitre in the 1920s and later refined and expanded upon by some of the greatest minds in science, is the prevailing cosmological model that explains the evolution of the universe from its earliest known states to the complex, diverse cosmos we inhabit today. But the story of the Big Bang is not one of certainty, but rather a tapestry of evidence, hypotheses, and ongoing scientific exploration. As we delve deeper into the mysteries of the universe, New discoveries and insights continue to shape and refine our understanding of this remarkable event that gave birth to all that we know. The foundation of the Big Bang Theory lies in the observation that the universe is expanding. In the 1920s, the renowned astronomer Edwin Hubble made a groundbreaking discovery. The galaxies beyond our own Milky Way were moving away from us, and the farther they were, the faster they were receding. This startling observation led to the realization that the universe was not static, as had long been assumed, but rather was in a constant state of expansion. Hubble's work, building upon the earlier theoretical work of Lemaitre, laid the groundwork for the Big Bang Theory, which posits that the entire universe originated from a single, infinitely dense point that exploded outward in a cataclysmic event. As the universe expanded, the initial incredibly hot and dense state of the cosmos began to cool, allowing for the formation of the first fundamental particles and the emergence of the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Over billions of years, this expanding and cooling universe gave rise to the galaxies, stars, and planets that we observe today, with the faint echoes of the Big Bang still detectable in the cosmic microwave background radiation, a pervasive glow of ancient light that permeates the entire universe. The Big Bang Theory is not simply a fanciful idea, but rather a robust and well-supported scientific model that is underpinned by a wealth of observational and experimental evidence. Let's explore some of the key pieces of evidence that lend credence to this remarkable theory. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, or CMB, which was first detected in 1964 by the American physicists Arno Penzias and Robert Wilson. This faint, uniform glow of radiation is believed to be the remnant of the intense heat and energy that filled the early universe, released when the cosmos was just 300,000 years old and had cooled enough for the first atoms to form. The CMB serves as a kind of fossil from the early universe, providing scientists with a snapshot of the universe's state shortly after the Big Bang. Detailed measurements of the CMB have revealed that it is remarkably uniform, with only tiny fluctuations in temperature that correspond to the seeds of the large-scale structures we observe in the universe today: the galaxies, galaxy clusters, and vast cosmic voids. Another key piece of evidence for the Big Bang is the observed abundance of the lightest elements in the universe, namely hydrogen, helium, and trace amounts of lithium. The Big Bang Theory predicts the relative proportions of these elements based on the extreme temperatures and densities that would have existed in the early universe, and the observed abundances are in remarkable agreement with these predictions. This process, known as Big Bang nucleosynthesis, demonstrates that the early universe was hot and dense enough to allow for the fusion of these lightweight elements, providing further validation of the Big Bang model. The observed redshift of light from distant galaxies, first noted by Hubble, also provides strong support for the Big Bang. As the universe expands, the wavelengths of light from these distant objects are stretched, or redshifted, in a manner that is consistent with the predictions of the Big Bang Theory. Furthermore, the distribution of galaxies and the large-scale structure of the universe, the filaments, voids, and clusters we observe, aligns remarkably well with the predictions of computer simulations based on the Big Bang model, reinforcing the validity of this cosmic origin story. One of the most profound and perplexing aspects of the Big Bang Theory is the notion that it represents the very origin of time and space itself. Prior to the Big Bang, the concept of time and space as we understand them simply did not exist. It was a state of pure, undifferentiated potential, a singularity where the laws of physics as we know them break down. In this initial state, the entire universe was compressed into a space so infinitely small that it is difficult for our minds to comprehend. all the matter and energy that would eventually make up the countless stars, galaxies, and cosmic structures we observe today was concentrated in a point of unimaginable density and heat. And then, in a cataclysmic event that defies our ability to fully visualize, this primordial state was shattered, giving rise to the expansion of space and the flow of time as we know it. The universe, born in a fiery explosion of unparalleled power, began to cool and evolve, eventually giving rise to the complex and diverse cosmos we inhabit today. This notion of the Big Bang as the very origin of time and space itself is a profound and humbling concept. It suggests that the universe, and indeed the very fabric of reality, had a distinct beginning, a moment when all of existence burst forth from an infinitesimal point. This has led to deep philosophical and theological questions about the nature of the universe, the role of causality, and the possibility of a creator or some other form of ultimate origin beyond the scope of scientific understanding. The Big Bang Theory, in a sense, has become a battleground for debates between science and various religious and metaphysical worldviews. Despite the wealth of evidence that supports the Big Bang Theory, there are still many unanswered questions and unresolved mysteries surrounding this remarkable event. As we continue to explore the depths of the cosmos, new discoveries and insights are constantly challenging and refining our understanding of the Big Bang and the origins of the universe. One of the most perplexing mysteries is the nature of the initial singularity, the infinitely dense and hot state that preceded the expansion of the universe. At this point, the laws of physics as we understand them break down, and our ability to comprehend the true nature of reality is pushed to its limits. What exactly was the state of the universe prior to the Big Bang? Was there a previous cycle of expansion and contraction, or did the universe truly emerge from nothing? These are questions that touch on the very limits of our scientific knowledge and the philosophical underpinnings of our understanding of the cosmos. Another major mystery is the nature of the initial conditions that led to the Big Bang. Why was the universe in such a highly ordered, low-entropy state at the moment of the Big Bang? This is a crucial question, as the second law of thermodynamics suggests that the universe should be in a state of higher disorder and chaos. The fact that the cosmos appears to have begun in a highly organized state is a puzzle that continues to challenge scientists. The issue of cosmic inflation, the remarkable period of exponential expansion that occurred in the first fraction of a second after the Big Bang, is another area of ongoing research and debate. While inflation provides a compelling explanation for the uniformity and large-scale structure of the universe, the precise mechanisms that drove this explosive expansion are not yet fully understood. Additionally, the nature of the mysterious dark matter and dark energy that appear to permeate and shape the universe on the grandest scales remains one of the greatest unsolved mysteries in modern cosmology. These unseen components make up the vast majority of the universe, yet their precise nature and origin continue to elude scientists. As we delve deeper into the mysteries of the Big Bang, new questions and challenges constantly arise. The more we learn, the more we realize how much we still have to discover about the origins and evolution of our universe. But it is precisely this sense of wonder and the thrill of the unknown that fuels the ongoing scientific exploration of the Big Bang and the ever-expanding frontiers of our cosmic understanding. The Big Bang Theory has not only transformed our understanding of the universe, but it has also had a profound impact on our very conception of reality, causality, and the nature of existence itself. This remarkably successful scientific model has become one of the cornerstones of modern cosmology, shaping the way we view the cosmos and our place within it. One of the most enduring legacies of the Big Bang is the way it has challenged our intuitions about the nature of time and space. The idea that the entire universe, including the very fabric of reality, emerged from a single infinitely dense point has forced us to rethink our most fundamental assumptions about the nature of existence. The notion that time and space had a beginning, that they emerged from a state where the laws of physics as we know them did not apply, has profound philosophical and theological implications. It has sparked debates about the role of causality, the possibility of a creator, and the very meaning of existence itself. Additionally, the Big Bang theory has transformed the way we approach the study of the universe. By providing a comprehensive model for the evolution of the cosmos, it has allowed scientists to make testable predictions and develop sophisticated computer simulations to better understand the complex structures and processes that shape the universe. Moreover, the ongoing exploration of the Big Bang and the early universe has led to remarkable advances in fields such as particle physics, astrophysics, and cosmology. The search for answers about the origins of the cosmos has driven the development of cutting-edge technologies and experimental techniques, pushing the boundaries of our scientific understanding. Indeed, the legacy of the Big Bang extends far beyond the realm of science. It has captured the public's imagination, inspiring countless works of art, literature, and popular culture. The idea of the universe emerging from a primordial infinitesimal point has become a powerful metaphor for the fragility and wonder of existence and has profoundly influenced our collective sense of place in the cosmos. As we continue to explore the mysteries of the Big Bang and the origins of the universe, we can be certain that this remarkable theory will continue to shape our understanding of the world around us, and perhaps even our deepest conceptions of the nature of reality itself. The Big Bang stands as a testament to the power of human curiosity and the relentless pursuit of knowledge, a cosmic drama that continues to unfold before our eyes. In the grand cosmic drama that unfolded with the explosive birth of our universe, the first few moments after the Big Bang were a whirlwind of extraordinary activity and transformation. From the initial, infinitely dense and hot state, the universe rapidly expanded and cooled, giving rise to the fundamental building blocks of matter and the fundamental forces that would shape the cosmos for billions of years to come. It was a period of pure potential, a time of unbridled creation, and the emergence of the very fabric of reality as we know it. In the blink of an eye, the universe transitioned from a state of unimaginable energy and density to one where the first subatomic particles began to form, setting the stage for the gradual coalescence of the structures we observe in the cosmos today. To truly understand the early universe is to peer into the very origins of existence itself. It is a journey through the formative moments that gave rise to the intricate and magnificent universe we inhabit, a tale of transformation and the birth of the fundamental constituents of matter and energy. In the very first instance after the Big Bang, the universe was in a state that defies our comprehension. Known as the Planck epoch, this initial period lasted for a mere 1/1,000,000,000 of a trillionth of a trillionth of a second, yet it was a moment of pure, unadulterated potential, the very beginning of time and space as we know them. During this fleeting moment, the entire universe was compressed into a state of unimaginable density and heat, where the very fabric of reality was pushed to its limits. The laws of physics as we understand them broke down, and the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified in a single, all-encompassing state. It was a state of pure, undifferentiated energy, where the distinctions between matter and energy, space and time, were blurred beyond recognition. The universe was a seething cauldron of primordial particles and fields, a maelstrom of pure potential waiting to be unleashed. And then, in a cataclysmic event that defies our ability to fully comprehend, the Planck epoch came to an end, ushering in the next phase of the universe's rapid transformation. As the cosmos expanded and cooled, the fundamental forces began to separate, and the first subatomic particles started to take shape, setting the stage for the emergence of the complex structures we observe in the present-day universe. In the wake of the Plague Epoch, the universe entered a period of remarkable and unprecedented expansion known as cosmic inflation. During this fleeting but transformative stage, the universe grew at a truly staggering rate, expanding by a factor of more than 100 trillion in a mere fraction of a second. This explosive growth was driven by a mysterious form of energy known as the inflationary field, which permeated the early universe and exerted a powerful repulsive force that drove the cosmos to expand at a rate far exceeding the speed of light. This rapid expansion smoothed out the initial irregularities in the distribution of matter and energy, creating the remarkably uniform universe we observe today. As the universe expanded, the inflationary field gradually dissipated, giving way to the formation of the first fundamental particles, quarks, leptons, and gauge bosons, and the emergence of the four fundamental forces that would shape the evolution of the cosmos. The inflationary epoch was a critical turning point in the history of the universe, a period of rapid transformation that laid the groundwork for the emergence of the complex structures we observe today. It was a time of pure potentiality, where the building blocks of reality were being forged in the crucible of the early universe. As the universe continued to expand and cool, the next phase of its transformation saw the emergence of the first fundamental particles, the quarks and leptons that would eventually come together to form the protons, neutrons, and other hadrons that make up the visible matter in the cosmos. In the intense heat and density of the early universe, these fundamental particles existed in a state known as the quark-gluon plasma, a primordial soup of quarks and gluons, the particles that bind quarks together to form more complex structures. Within this quark-gluon plasma, the fundamental forces began to separate, and the strong nuclear force, which binds quarks together, emerged as a distinct and powerful force. As the universe continued to expand and cool, the quarks and gluons began to coalesce, forming the first protons and neutrons in a process known as hadronization. This transition from the quark-gluon plasma to the formation of the first hadrons was a crucial step in the evolution of the early universe, setting the stage for the emergence of the atoms and molecules that would eventually give rise to the complex structures we observe today. The study of the quark-gluon plasma has become a major focus of modern particle physics, as researchers use powerful particle accelerators to recreate this primordial state of matter and unlock the secrets of the early universe. By understanding the behavior of quarks and gluons under extreme conditions, scientists hope to gain deeper insights into the fundamental nature of matter and the origins of the cosmos. As the universe continued to expand and cool, the next critical milestone in its evolution was the decoupling of matter and radiation, a pivotal moment when the primordial soup of particles and energy began to separate, paving the way for the formation of the first atoms and the emergence of a transparent universe. Prior to this decoupling, the universe was a roiling cauldron of charged particles and radiation, where the intense interactions between matter and photons kept the cosmos in a state of perpetual opacity. Photons were constantly scattering off electrons and other charged particles, preventing the free propagation of light and effectively trapping the energy of the early universe in a dense, opaque fog. However, as the universe expanded and cooled, the temperature dropped to the point where the first atoms could begin to form. As neutral atoms emerged, the interactions between matter and radiation began to diminish, allowing the photons to decouple from the matter and travel freely through the cosmos. This moment of decoupling, which occurred when the universe was approximately 300,000 years old, marked a profound transformation in the nature of the cosmos. The universe went from being a hot, dense, and opaque plasma to a transparent, gas-like state, where the first structures began to take shape and the cosmic microwave background radiation was released, providing a snapshot of the early universe. The decoupling of matter and radiation is a crucial milestone in the history of the cosmos, as it represents the transition from the primordial, featureless state of the early universe to the complex, structured universe we observe today. It was a pivotal moment that paved the way for the formation of the first stars and galaxies and the eventual emergence of the rich tapestry of cosmic structures that we see in the present-day universe. Following the decoupling of matter and radiation, the universe entered a critical phase known as the epoch of recombination, a time when the first stable atoms began to form, marking a profound transformation in the nature of the cosmos. Prior to this epoch, the universe was dominated by a hot, dense plasma of charged particles, protons, neutrons, and electrons, that were constantly interacting with photons, preventing the free propagation of light. However, as the universe expanded and cooled, the temperature dropped to the point where the electrons could become bound to the nuclei of the first atoms, creating neutral hydrogen and helium. This process of recombination, in which the charged particles were able to form stable, neutral atoms, was a pivotal moment in the evolution of the cosmos. It allowed the photons that had previously been trapped in the primordial plasma to decouple from the matter, streaming freely through the universe and forming the cosmic microwave background radiation that we observe today. The epoch of recombination was a time of profound transformation as the universe transitioned from a hot, dense, opaque state to one that was cool, transparent, and filled with the first atoms. This marked the end of the so-called Dark Ages of the universe, a period when the cosmos was completely dark, devoid of the luminous structures we observe today. As the first atoms formed, the universe became increasingly transparent, allowing gravity to begin shaping the distribution of matter and energy. This set the stage for the eventual formation of the first stars, galaxies, and other complex structures that would populate the cosmos in the billions of years to come. The epoch of recombination, with its transition from a plasma-dominated universe to one filled with neutral atoms, is a crucial milestone in the history of the cosmos, representing a pivotal turning point in the evolution of the early universe. After the remarkable transformations of the early universe, with the formation of the first fundamental particles, the emergence of the four fundamental forces, and the decoupling of matter and radiation, the cosmos continued to expand and cool, setting the stage for the eventual formation of the complex structures we observe today. As the universe expanded, the temperature of the primordial plasma continued to drop, allowing the first stable atoms to form during the epoch of recombination. This transition marked the end of the so-called Dark Ages of the universe, a period when the cosmos was completely dark and devoid of the luminous structures we observe today. With the formation of the first atoms, the universe became increasingly transparent, allowing gravity to begin shaping the distribution of matter and energy. This set the stage for the eventual formation of the first stars, galaxies, and other complex structures that would populate the cosmos in the billions of years to come. The continued expansion and cooling of the universe also led to the gradual separation of the fundamental forces, with gravity, electromagnetism, the strong nuclear force, and the weak nuclear force each exerting their influence on the evolving cosmic structures. As the universe expanded, the density of matter and energy decreased, and the once unified fundamental forces began to manifest as distinct and independent phenomena. This process of force separation was a crucial step in the development of the universe, as it allowed the various components of matter and energy to interact in the complex ways that gave rise to the rich tapestry of cosmic structures we observe today. The aftermath of the early universe's transformation was a period of profound and ongoing change as the cosmos continued to evolve and grow, fueled by the fundamental forces and the intricate interplay of matter and energy. This period set the stage for the eventual formation of the first stars and galaxies, the emergence of complex structures, and the gradual development of the universe we inhabit today. Through the study of the early universe and its aftermath, scientists have gained invaluable insights into the nature of reality, the origins of the cosmos, and the fundamental forces that shape the universe. The story of the early universe is one of profound transformation and the gradual unfolding of the complex and magnificent cosmos we call home. Among the countless wonders of the cosmos, few captivate the human imagination quite like the life and death of the stars. These luminous celestial bodies, shining beacons in the vast darkness of the universe, are the engines that drive the grand cosmic drama, forging the very building blocks of existence and shaping the evolution of galaxies. To gaze up at the night sky and behold the twinkling stars is to peer into the past, to glimpse the powerful forces that have been at work since the dawn of time. For the life cycle of a star is a story of birth, growth, and eventual demise, a saga that unfolds over billions of years, shaped by the fundamental laws of physics and the intricate dance of matter and energy. From the billowing clouds of gas and dust that give rise to new stars, to the cataclysmic explosions that mark the end of a stellar life, the journey of a star is a testament to the dynamic, ever-changing nature of the universe. It is a tale of transformation and the delicate balance between creation and destruction, a cycle that has played out countless times throughout the cosmos, giving birth to the very elements that make up our world and the worlds around us. The story of a star's life begins not with the star itself, but in the vast, nebulous regions of space where stars are born. These stellar nurseries, known as nebulae and molecular clouds, are the vast, billowing expanses of gas and dust that serve as the raw materials for the formation of new stars. Composed primarily of hydrogen and helium, with trace amounts of heavier elements, these celestial nurseries are the harbingers of creation, the cosmic wombs where the next generation of stars will take shape. Powered by the gravitational attraction of their own mass, these immense clouds slowly collapse, fragmenting and condensing into dense pockets of matter that will eventually give rise to the stars we observe in the night sky. It is within these dense, shrouded regions that the process of star formation begins, as the force of gravity pulls the matter inward, generating heat and pressure that will ultimately ignite the nuclear fusion that powers a star's life. Over thousands, even millions of years, these clouds of gas and dust transform, their once diffuse structures coalescing into the bright, luminous stars that illuminate the cosmos. The diversity of nebulae and molecular clouds is a testament to the dynamic nature of the star formation process. From the vast, sprawling structures of the Orion Nebula to the ethereal, billowing clouds of the Carina Nebula, each stellar nursery is a unique, constantly evolving environment shaped by the interplay of gravity, radiation, and the explosive energy of nearby stars. It is within these cosmic wombs that the story of a star's life begins, a journey that will take it through the various stages of stellar evolution, from the luminous infancy of a newborn star to the cataclysmic demise that marks the end of its existence. Once a star has been born, it embarks on the longest and most stable phase of its life cycle, the main sequence. This is the period during which a star will spend the majority of its existence, fusing hydrogen into helium at its core and radiating energy into the surrounding universe. The main sequence is a delicate balancing act, a harmonious interplay between the inward pull of gravity and the outward pressure of the nuclear fusion reactions taking place at the star's core. As the star's core contracts and heats up, the pressure and temperature increase, triggering the fusion of hydrogen into helium, releasing energy that counteracts the force of gravity and keeps the star in a state of stable equilibrium. This dynamic equilibrium is the hallmark of a main sequence star, and it is the stage during which a star will spend the majority of its life, typically ranging from millions to billions of years, depending on the star's mass and composition. During this time, the star will maintain a consistent brightness and color, its energy output driven by the steady fusion of hydrogen into helium at its core. The precise duration of a star's main sequence lifetime is determined by its mass. The more massive the star, the shorter its lifespan. This is because more massive stars burn through their hydrogen fuel at a much faster rate, with the most massive stars burning through their reserves in just a few million years, while smaller, less massive stars can remain in the main sequence for tens of billions of years. As a star progresses through the main sequence, it will undergo subtle changes in its structure and appearance. The core will gradually become more dense and hot, while the outer layers will expand and cool, resulting in a shift in the star's color and luminosity. These changes are a reflection of the ongoing nuclear fusion processes taking place within the star's interior, as it slowly but inexorably consumes its hydrogen fuel. The main sequence, with its steady, reliable energy output, is the foundation upon which the complex structures of the cosmos are built. It is the stage during which stars provide the illumination and heat that nourish the development of planets, moons, and the intricate web of galaxies that populate the universe. And it is during this chapter in a star's life cycle that the most remarkable and diverse phenomena of stellar evolution begin to unfold. While the main sequence represents the longest and most stable phase of a star's life, it is by no means the only chapter in the story of a star's evolution. As a star consumes its hydrogen fuel and its core undergoes changes, it will transition through a series of remarkable transformations, each one marked by unique and often dramatic phenomena. As a star nears the end of its main sequence lifespan, the core will begin to contract and heat up, triggering the fusion of helium into heavier elements like carbon and oxygen. This shift in the star's internal structure leads to the expansion of its outer layers, transforming the star into a red giant, a luminous, bloated, and often unstable phase of a star's life. The red giant phase is a period of profound change as the star's outer layers swell to immense proportions, sometimes engulfing nearby planets in the process. During this time, the star's energy output can increase dramatically, creating a powerful stellar wind that can strip away material from the star's surface. For some stars, the red giant phase is a relatively brief and stable transition, while for others, it can be a tumultuous and unpredictable period, marked by dramatic flares, pulsations, and even the ejection of material from the star's outer layers. These dynamic events are a testament to the complex interplay of forces that govern the life and death of a star. As the red giant phase comes to an end, the star's fate will depend largely on its mass. Lower mass stars, like our Sun, will eventually shed their outer layers, forming a dense hot core known as a white dwarf. These compact, dense objects are the final stage in the life cycle of many stars, slowly radiating away their remaining energy over billions of years. For more massive stars, however, the story takes a more dramatic turn. As the core of a massive star continues to contract and heat up, it can trigger the fusion of even heavier elements, like carbon, neon, and silicon. This process, known as nuclear shell burning, can lead to a series of explosive events, including the dramatic supernova, the catastrophic end of a star's life. Supernovae are among the most awe-inspiring and powerful phenomena in the universe, releasing an incredible amount of energy as the star's core collapses and the outer layers are ejected into the cosmos. These cataclysmic events play a crucial role in the evolution of the universe, seeding the surrounding space with the heavy elements that are essential for the formation of planets, moons, and even life itself. The diverse stages of stellar evolution, from the main sequence to the dramatic end-of-life events, are a testament to the dynamic and ever-changing nature of the cosmos. Each phase of a star's life cycle, whether it be the steady glow of a main sequence star or the explosive finale of a supernova, is a unique and captivating chapter in the grand cosmic saga. Throughout the various stages of their life cycles, stars can exhibit a remarkable range of phenomena, each one reflecting the complex interplay of the fundamental forces that govern the universe. From the subtle pulsations of variable stars to the dramatic outbursts of supernovae, the diversity of stellar phenomena, is a testament to the incredible complexity of the cosmos. One of the most fascinating and diverse categories of stellar phenomena is that of variable stars, stars whose brightness fluctuates over time, often in patterns that can reveal important information about their internal structure and evolutionary state. These variable stars can be classified into numerous subtypes, each with its own unique characteristics. Some variable stars, like the Cepheid variables, exhibit a regular, predictable pattern of brightness changes, their luminosity rising and falling in perfect synchronization with their internal pulsations. These pulsating variables play a crucial role in the study of cosmic distances, as their period-luminosity relationship allows astronomers to use them as standard candles to measure the distances to distant galaxies. Other variable stars, like the Mira variables, undergo more dramatic and irregular changes in brightness, a reflection of the complex processes unfolding within their stellar interiors. These variables, which can increase in brightness by dozens of times over the course of their cycles, provide valuable insights into the late stages of stellar evolution, as the star's outer layers are shaped by powerful stellar winds and convection currents. Beyond the variable stars, the cosmos is home to an even more dramatic and explosive class of stellar phenomena, the various types of supernovae. These cataclysmic events, which mark the end of a star's life, come in several distinct flavors, each one reflecting the unique circumstances that led to the star's demise. Type Is supernovae, for example, are the result of a white dwarf star accumulating material from a companion star until it reaches a critical mass, triggering a runaway nuclear explosion. These supernovae are remarkably consistent in their brightness, making them valuable tools for measuring cosmic distances and the acceleration of the universe's expansion. In contrast, Type Ia supernovae occur when the core of a massive star collapses under its own gravity, triggering a catastrophic explosion that blasts the star's outer layers into the surrounding space. These events are the final chapter in the life of stars, much more massive than our Sun, and they play a crucial role in seeding the cosmos with the heavy elements essential for the formation of planets, moons, and life. The diversity of stellar phenomena is a testament to the incredible complexity of the universe and the ongoing efforts of astronomers and astrophysicists to unravel the mysteries of these celestial wonders. From the subtle pulsations of variable stars to the explosive grandeur of supernovae, each unique stellar event offers a window into the dynamic and ever-changing nature of the cosmos and the fundamental forces that shape the life and death of the stars. As we gaze out into the vast expanse of the night sky, our eyes are drawn to the countless points of light that twinkle and shine, each one a testament to the grandeur and complexity of the universe. But these stars, the familiar beacons that have captivated humanity for millennia, are merely the tip of the cosmic iceberg. For beyond these individual luminous bodies lie the true engines of the universe, the galaxies, the vast and sprawling structures that serve as the building blocks of the cosmos. Galaxies, those magnificent celestial islands that populate the void of intergalactic space, are the result of a truly remarkable process of cosmic evolution, a story that spans billions of years and encompasses the birth and death of stars, the ebb and flow of matter and energy, and the fundamental forces that shape the very fabric of reality. To understand the formation of galaxies is to peer into the very origins of the universe itself, to unravel the mysteries of how the first complex structures emerge from the primordial chaos of the Big Bang. It is a tale of gravity, dark matter, and the intricate dance of matter and radiation that gave rise to the diverse tapestry of galaxies we observe today. The story of galaxy formation begins in the earliest moments of the universe, in the wake of the cataclysmic Big Bang that gave birth to space, time, and the fundamental particles that would eventually coalesce into the structures we recognize today. In the immediate aftermath of the Big Bang, the universe was a hot, dense soup of elementary particles and radiation, a state so extreme that the fundamental forces of nature were unified in a single, all-encompassing state. As the universe expanded and cooled, however, these forces began to separate, and the first subatomic particles, protons, neutrons, and electrons, began to form. It was during this critical phase, known as the epoch of recombination, that the first structures in the universe began to take shape. As the cosmos continued to expand and cool, the primordial soup of particles and radiation became increasingly transparent, allowing gravity to exert its influence and shape the distribution of matter. Regions of slightly higher density, seeded by tiny quantum fluctuations in the early universe, began to attract more matter through the force of gravity, forming the first proto-galaxies, the embryonic structures that would eventually grow into the majestic, spiral-armed behemoths that populate the cosmos today. These proto-galaxies, tiny clumps of matter and dark matter that served as the building blocks of the larger cosmic structures, were the result of a delicate interplay between the fundamental forces and the expansion of the universe. As gravity pulled matter together, the expansion of space worked to disperse it, creating a dynamic equilibrium that would ultimately give rise to the first true galaxies. Central to the story of galaxy formation is the mysterious and elusive substance known as dark matter. This invisible yet immensely influential component of the universe makes up the vast majority of the matter in the cosmos, exerting a powerful gravitational influence that has shaped the distribution and evolution of galaxies since the earliest stages of the universe. Dark matter, which does not interact with electromagnetic radiation and is therefore invisible to our telescopes, acts as a kind of cosmic scaffolding, providing the framework upon which galaxies and larger cosmic structures are built. As the proto-galaxies formed in the aftermath of the Big Bang, the gravitational pull of the dark matter served to draw in and condense the baryonic matter, the familiar protons, neutrons, and electrons that make up the visible universe. Without the gravitational influence of dark matter, the formation of galaxies would have been a vastly different process, one in which the matter would have been too diffuse and dispersed to coalesce into the intricate, spiral-armed structures we observe today. It is the interplay between the visible matter and the unseen dark matter that has been the driving force behind the birth and evolution of galaxies, from the earliest proto-galaxies to the magnificent spirals and ellipticals that populate the modern universe. As astronomers continue to study the distribution of dark matter in the cosmos, they are gaining invaluable insights into the processes that have shaped the galactic landscape. By mapping the dark matter halos that surround and permeate galaxies, scientists can better understand the complex dynamics that have led to the diverse array of galactic morphologies we observe, from the elegant spiral arms of the Milky Way to the massive elliptical behemoths that dominate galaxy clusters. The role of dark matter in galaxy formation is a testament to the interconnectedness of the universe, a reminder that the visible world we inhabit is but a small fraction of the cosmic tapestry, woven together by the unseen forces that have guided the evolution of galaxies and the structures that populate the vast expanses of intergalactic space. As the first proto-galaxies coalesced and grew in the early universe, they began to take on a variety of distinct morphologies, each one reflecting the unique circumstances and processes that shaped their formation and evolution. Perhaps the most iconic and well-known class of galaxies are the spiral galaxies, majestic structures characterized by their swirling, pinwheel-like arms that emanate from a central bulge. These spirals, of which our own Milky Way is a member, are the product of a delicate balance between the gravitational forces that shape their structure and the complex dynamics of the stars, gas, and dust that make up their components. The spiral arms of these galaxies are thought to be the result of density waves, regions of slightly higher density that propagate through the disk of the galaxy, triggering the formation of new stars and the accumulation of gas and dust. As these density waves move through the galactic disk, They create the illusion of spiraling arms, a mesmerizing and visually striking feature of these cosmic structures. In contrast to the spiral galaxies, the elliptical galaxies are characterized by their more rounded, amorphous shapes, with little to no discernible structure beyond a smooth elliptical profile. These galaxies, which can range from the relatively small and compact to the truly massive and dominating, are thought to be the product of galaxy mergers, where two or more spiral or irregular galaxies have collided and coalesced over billions of years. The process of galaxy mergers is a crucial driver of the evolution of galactic structures, as the collisions and interactions between these cosmic giants can dramatically reshape their morphologies, giving rise to the diverse array of elliptical, lenticular, and even irregular galaxies we observe in the present-day universe. Beyond the spirals and ellipticals, the cosmos is also home to a variety of other galactic types, each one reflecting the unique circumstances of its formation and evolution. Irregular galaxies, for example, are chaotic, asymmetrical structures that lack the well-defined shapes of their spiral and elliptical counterparts, often the result of the gravitational disruption caused by interactions with neighboring galaxies. The diversity of galactic morphologies is a testament to the complex and dynamic processes that have shaped the evolution of the cosmos, from the earliest proto-galaxies to the magnificent structures we observe today. By studying the various galactic types and their distributions throughout the universe, astronomers can gain valuable insights into the fundamental forces and interactions that have guided the formation and growth of these cosmic lighthouses. As the universe has expanded and evolved over billions of years, the formation and growth of galaxies has been a dynamic and hierarchical process, with smaller structures coalescing and merging to form the larger, more complex structures we observe today. This hierarchical assembly of galaxies is a crucial aspect of the cosmic story, as it reflects the interplay between the fundamental forces of nature and the expansion of the universe. In the early universe, the first proto-galaxies formed from the gravitational collapse of slightly denser regions in the primordial soup of matter and radiation. As these proto-galaxies grew in size and mass, they began to attract and merge with their neighbors, forming larger and more complex structures. Over time, this process of merging and accretion continued, with the smaller galaxies being drawn into the gravitational fields of their larger counterparts, creating the intricate web of galactic structures that we observe in the present-day universe. This hierarchical assembly is a key driver of the evolution of galaxies, as the collisions and interactions between these cosmic giants can dramatically reshape their morphologies, giving rise to the diverse array of spiral, elliptical, and irregular galaxies we see today. The process of galaxy mergers is not only a crucial aspect of the hierarchical assembly of larger structures, but it also plays a vital role in the evolution of the individual galaxies themselves. As two or more galaxies collide, the resulting interactions can trigger a surge of star formation, as the gravitational forces and compression of the gas and dust within the galaxies ignite new generations of stars. Moreover, the merging of galaxies can also lead to the growth and evolution of the central supermassive black holes that reside at the heart of most galaxies. As the galaxies collide, their central black holes can also merge, resulting in the formation of even more massive black holes that can then go on to influence the subsequent evolution of the newly formed galactic structure. The hierarchical assembly of galaxies is a testament to the dynamic and ever-changing nature of the cosmos, a process that has played out over billions of years and continues to shape the cosmic landscape we observe today. By studying the distribution and properties of galaxies throughout the universe, astronomers can gain valuable insights into the fundamental forces and processes that have guided the formation and growth of these magnificent cosmic structures. The formation and evolution of galaxies is not merely a story of individual celestial structures, but rather a crucial component of the grand, large-scale architecture of the universe itself. The galaxies that populate the cosmos are not isolated entities, but rather part of a complex and interconnected web of matter and energy that stretches out across the vast expanse of intergalactic space. This large-scale structure of the universe, as it is known, is characterized by the intricate distribution of galaxies, galaxy clusters, and vast, sprawling filaments of dark matter and gas that form the cosmic scaffolding upon which the visible universe is built. It is a structure that has been shaped by the fundamental forces of nature, the expansion of the universe, and the hierarchical assembly of galaxies over billions of years. At the largest scales, the universe appears to be organized into a vast, interconnected network of filaments and sheets, with galaxies and galaxy clusters concentrated along these structures and vast, relatively empty voids in between. This cosmic web is a direct reflection of the initial conditions of the universe, with the tiny density fluctuations in the primordial matter distribution being amplified by the force of gravity over cosmic time. As the universe has expanded, these initial density variations have been stretched and shaped into the intricate web-like structures we observe today, with the galaxies and larger cosmic structures serving as the nodes and hubs of this vast, interconnected system. It is within this cosmic web that the individual galaxies and galaxy clusters reside, their formation and evolution inextricably linked to the larger-scale structure of the universe. The study of the large-scale structure of the cosmos is a crucial aspect of modern cosmology, as it provides valuable insights into the fundamental nature of the universe, the distribution of matter and energy, and the role of dark matter in shaping the structures we observe. By mapping the locations and properties of galaxies throughout the universe, astronomers can gain a better understanding of the underlying forces and processes that have guided the evolution of the cosmos over billions of years. From the earliest proto-galaxies to the magnificent spirals and ellipticals that populate the present-day universe, the formation and evolution of galaxies is a story of remarkable complexity and interconnectedness. It is a tale of the fundamental forces of nature, the mysterious influence of dark matter, and the dynamic, ever-changing nature of the cosmos. A story that continues to unfold before our eyes as we peer deeper into the infinite expanse of the universe. As we gaze up at the night sky, one celestial feature stands out among the countless stars and galaxies that populate the cosmos: the grand, luminous band of the Milky Way. This awe-inspiring sight, a vast, glowing river of light that arches across the heavens, is not merely a beautiful sight to behold. It is the very galaxy that we call home, the cosmic structure that has shaped the evolution of our solar system and all the life that inhabits our planet. The Milky Way, a spiral galaxy that is home to hundreds of billions of stars, is a truly remarkable and complex structure, one that has captivated the human imagination for millennia. From the ancient stargazers of antiquity to the modern astronomers who study its intricate details, the Milky Way has been a source of wonder, fascination, and an endless well of scientific discovery. To delve into the study of the Milky Way is to embark on a journey of cosmic proportions, to peel back the layers of this magnificent galactic structure and uncover the secrets that lie at the heart of our celestial home. It is a tale of star formation and stellar evolution, of dark matter and the fundamental forces that govern the universe, and of the intricate interplay between the Milky Way and the larger cosmic tapestry in which it is woven. At its core, the Milky Way is a spiral galaxy, a majestic structure characterized by its swirling, pinwheel-like arms that emanate from a central bulge. This central bulge, a densely packed region of mostly older, redder stars, is surrounded by a vast, disk-like structure composed of younger, hotter stars, as well as vast clouds of gas and dust that serve as the raw materials for ongoing star formation. Extending out from the galactic disk are the Milky Way's spiral arms, sweeping, luminous features that are home to some of the most active and dynamic regions of star birth and stellar evolution in our galaxy. These spiral arms, which are thought to be the result of density waves propagating through the disk, are the sites of intense star-forming activity, with vast clouds of gas and dust collapsing under their own gravity to give rise to new generations of stars. Surrounding the disk and central bulge of the Milky Way is a spherical halo, a diffuse and sparsely populated region that extends for thousands of light years in all directions. This halo is home to some of the oldest stars in the galaxy, as well as the mysterious and elusive dark matter that is believed to make up a significant portion of the Milky Way's total mass. But the Milky Way is not merely a static structure. It is a dynamic, ever-evolving entity, with the various components of the galaxy constantly interacting and shaping one another. The spiral arms, for example, are thought to be the result of the interplay between the gravitational forces that govern the galactic disk and the complex motions of the individual stars that make up the Milky Way. Similarly, the central bulge of the galaxy is believed to have been shaped by the merger and interaction of smaller, pre-existing galaxies, a process that has not only contributed to the formation of the bulge, but has also had a profound impact on the distribution and properties of the stars within the Milky Way. The composition of the Milky Way is equally complex and diverse, with the galaxy containing a vast array of stellar types, from the bright, massive stars that dominate the spiral arms to the ancient, low-mass stars that make up the majority of the halo. Additionally, the galaxy is host to a range of other celestial objects, including globular clusters, nebulae, and the supermassive black hole that resides at the very heart of the Milky Way. While the Milky Way may be our own cosmic home, it is but one small part of the grand, interconnected structure of the universe. As a spiral galaxy, the Milky Way is just one of countless such structures that populate the observable cosmos, each one a unique and complex entity shaped by the fundamental forces of nature and the intricate dance of matter and energy that has unfolded over billions of years. The Milky Way's place in the larger cosmic tapestry is a testament to the hierarchical nature of galactic formation and evolution. Just as the Milky Way is composed of countless stars, gas, and dust, so too is it part of a larger network of galaxies, galaxy clusters, and superclusters that stretch out across the vast expanse of intergalactic space. At the largest scales, the Milky Way and its neighboring galaxies are part of a group known as the Local Group, a collection of around 50 galaxies that are gravitationally bound to one another. This local group, in turn, is part of an even larger structure known as the Virgo supercluster, a vast, sprawling network of galaxy clusters and filaments that spans millions of light years across. The Milky Way's position within this cosmic hierarchy is not merely a matter of scale, but rather a reflection of the fundamental processes that have shaped the evolution of the universe. The formation and growth of the Milky Way, like that of all galaxies, is intimately linked to the distribution of dark matter, the mysterious and invisible substance that makes up the majority of the universe's mass. It is the gravitational influence of dark matter that has guided the hierarchical assembly of cosmic structures, from the first proto-galaxies that formed in the wake of the Big Bang to the vast, interconnected web of galaxies and galaxy clusters that we observe today. And it is within this cosmic scaffolding that the Milky Way has taken shape, its own evolution shaped by the ebb and flow of matter and energy that has unfolded over billions of years. As the home of our solar system and the planet Earth, the Milky Way galaxy holds a special place in the hearts and minds of humanity. But beyond its personal significance, the Milky Way also plays a crucial role in the search for habitable worlds beyond our own, serving as a laboratory for the study of the formation and evolution of planetary systems. Within the vast, disk-like structure of the Milky Way, our solar system is just one of countless planetary systems that have coalesced around the stars that populate the galaxy. And as astronomers continue to explore and study the diverse array of exoplanets that orbit these distant suns, they are gaining invaluable insights into the processes that shape the formation and evolution of planetary bodies. From the hot, rocky worlds that orbit perilously close to their host stars to the vast, icy giants that dwell in the outer reaches of their solar systems, the exoplanets discovered within the Milky Way have revealed a remarkable diversity of planetary environments. And as the search for habitable worlds beyond Earth continues, the Milky Way has emerged as a crucial testing ground for the theories and models that seek to explain the conditions necessary for the emergence of life. Indeed, the very location of our solar system within the Milky Way, nestled in the outer reaches of the galactic disk, far from the intense radiation and gravitational influences of the central bulge, may have played a crucial role in the development of life on Earth. By occupying a relatively peaceful and stable region of the galaxy, our planet has been shielded from the more extreme cosmic events that can threaten the existence of complex life. But the Milky Way's significance in the search for habitable worlds extends beyond the mere fact of our own existence. By studying the distribution and properties of exoplanets throughout the galaxy, astronomers are gaining a better understanding of the factors that influence planetary formation and the conditions that are most conducive to the emergence of life. From the role of stellar metallicity and the presence of gas giants in shaping planetary systems to the impact of cosmic radiation and the ebb and flow of matter and energy on the long-term habitability of worlds, the Milky Way serves as a vast and invaluable laboratory for the study of life in the universe. As our understanding of the Milky Way and its countless planetary systems continues to evolve, the search for habitable worlds beyond Earth is likely to become increasingly focused and targeted, with the knowledge gained from the study of our own cosmic home informing the strategies and technologies employed in the quest to discover signs of life elsewhere in the galaxy. At the very heart of the Milky Way galaxy lies one of the most fascinating and enigmatic objects in the entire cosmos, the supermassive black hole known as Sagittarius A*. This colossal, gravitationally dominant structure, which resides at the exact geometric center of our galaxy, is a testament to the incredible power and influence that black holes can exert on the surrounding universe. Sagittarius A, or Scar A for short, is a truly remarkable celestial body, with a mass estimated to be around 4 million times greater than that of our own Sun. This immense gravitational behemoth, a point of no return from which not even light can escape, serves as the gravitational anchor for the Milky Way, influencing the motion and behavior of the stars, gas, and dust that make up the heart of our galactic home. The presence of this supermassive black hole at the center of the Milky Way has had a profound impact on the evolution and structure of the galaxy, serving as a hub around which the various components of the Milky Way orbit and interact. The intense gravitational forces exerted by Scar A have played a crucial role in shaping the central bulge of the galaxy, as well as the complex motions and dynamics of the stars and stellar clusters that populate this region. Moreover, the activity and behavior of Sagittarius A itself has been the subject of intense scientific study, as astronomers seek to unravel the mysteries of these enigmatic cosmic entities. Through observations of the material that is swallowed and accreted by the black hole, as well as the energetic outbursts and jets that can emanate from its vicinity, scientists have gained invaluable insights into the physics of black holes and their role in the larger cosmic landscape. Indeed, the study of Sagittarius A has been crucial in the development of our understanding of black holes, from the confirmation of their existence as predicted by Einstein's theory of general relativity to the exploration of the extreme conditions that exist in the immediate vicinity of these gravitational behemoths. As the focal point of the Milky Way, Sagittarius A serves as a constant reminder of the incredible power and influence that black holes can exert on the evolution of galaxies. And as astronomers continue to study this enigmatic object and its interactions with the surrounding material, they are sure to uncover even more secrets about the nature of these cosmic titans and their place at the heart of our own galactic home. While the Milky Way may be our own cosmic home, it is but one small part of a much larger and more complex cosmic landscape. Beyond the boundaries of our galaxy, the universe teems with countless other galactic structures, each one a unique and fascinating entity shaped by the fundamental forces of nature and the intricate dance of matter and energy that has unfolded over billions of years. The Milky Way, as it turns out, is not alone in its cosmic neighborhood. Indeed, it is part of a larger gravitationally bound group of galaxies known as the Local Group, a collection of around 50 individual galaxies that are bound together by the mutual pull of their combined gravitational fields. At the heart of the Local Group is the Andromeda Galaxy, or M31, a massive spiral galaxy that is the Milky Way's closest galactic neighbor, located a mere 2.5 million light-years away. This colossal structure, which is similar in size and composition to our own galaxy, is the dominant member of the Local Group, exerting a significant gravitational influence on the other galaxies that make up this cosmic community. Beyond the Andromeda Galaxy, the Local Group also contains a number of smaller dwarf galaxy companions, including the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere. These diminutive structures, which are gravitationally bound to the Milky Way and Andromeda, provide valuable insights into the processes of galaxy formation and evolution, as well as the role of dark matter in shaping the cosmic landscape. But the Local Group is just one small part of an even larger cosmic structure known as the Virgo supercluster, a vast, sprawling network of galaxy clusters and filaments that spans millions of light-years across. This Virgo supercluster, of which the Local Group is but a small component, is part of an even grander cosmic web that stretches out across the observable universe, a tapestry of galaxies, dark matter, and the fundamental forces that have guided the evolution of the cosmos. By studying the Milky Way and its cosmic neighbors, astronomers have gained invaluable insights into the processes that have shaped the structure and evolution of the universe as a whole. From the role of dark matter in the formation and growth of galaxies to the intricate web of gravitational interactions that bind these cosmic structures together, the study of the Milky Way and its place in the larger cosmic landscape has been a crucial component of our understanding of the universe. As we continue to explore the Milky Way and the myriad of other galaxies that populate the observable cosmos, we are sure to uncover even more secrets about the fundamental nature of the universe and the processes that have given rise to the incredible diversity of cosmic structures we observe today. As we gaze up at the Milky Way, it is easy to think of our galactic home as a fixed, eternal structure, a timeless celestial beacon that has shone in the night sky for billions of years. But the truth is, the Milky Way is a dynamic and ever-evolving entity, shaped by the constant interplay of gravity, matter, and energy that defines the cosmos. And one of the most significant events in the Milky Way's future is the impending collision with its closest neighbor, the Andromeda Galaxy. This titanic merger, which is predicted to occur in a staggering 4.5 billion years, will have a profound and lasting impact on the structure and evolution of our galactic home. As the two massive spiral galaxies draw closer together, their gravitational fields will begin to interact, causing the stars, gas, and dust within each galaxy to become distorted and reshuffled. Over time, the individual structures of the Milky Way and Andromeda will begin to blend together, forming a single elliptical-shaped galaxy that will be even more massive and dominant than either of the two original spirals. This galactic collision, which astronomers have dubbed the Milky-Meta merger, will have far-reaching consequences for the stars and planetary systems that call the Milky Way home. The gravitational forces unleashed by the merger will likely disrupt the orbits of many of the stars in our solar neighborhood, potentially sending some of them hurtling out into the intergalactic void, while others may be drawn in closer to the central region of the newly formed galaxy. Moreover, the intense bursts of star formation that are predicted to accompany the merger may dramatically reshape the distribution and properties of the stars within the Milky Way, with the possibility of new generations of stars forming from the gas and dust that is stirred up by the collision. But the Milkomeda merger is just one chapter in the Milky Way's long and eventful future. Even after this titanic event, our galactic home will continue to evolve, with the combined galaxy likely to interact with and merge with other nearby structures, further shaping the cosmic landscape. Indeed, the ultimate fate of the Milky Way and the Andromeda Galaxy is far from certain, as the ever-accelerating expansion of the universe and the mysterious influence of dark energy may have profound and unpredictable effects on the long-term evolution of these cosmic giants. As we contemplate the future of the Milky Way, it is a humbling reminder that our galactic home, for all its grandeur and majesty, is but a fleeting and transient component of the larger cosmic drama that has unfolded over billions of years. And yet, the study of the Milky Way and its place in the universe remains a crucial endeavor, one that continues to reveal the fundamental secrets of the cosmos and our own origins as a species, from the swirling spiral arms that give the Milky Way its iconic appearance to the towering supermassive black hole that anchors its heart. This magnificent galaxy is a testament to the incredible complexity and beauty of the universe we inhabit. And as we continue to unravel its mysteries, we are sure to unlock even greater insights into the nature of existence itself. In the grand tapestry of the cosmos, the visible universe we observe, the galaxies, stars, and planets that populate the night sky, is but a mere fraction of the true nature of reality. Underlying the familiar structures we see with our telescopes and instruments lies an unseen and mysterious realm, a hidden component of the universe that has eluded our understanding for decades, yet exerts a profound influence on the very fabric of existence. This unseen realm is the domain of dark matter and dark energy, two of the most perplexing and enigmatic concepts in modern cosmology. Together, these mysterious entities make up the vast majority of the universe, accounting for over 95% of the total mass and energy that shapes the cosmos we inhabit. And yet, despite their overwhelming dominance, the true nature of dark matter and dark energy remains one of the greatest unsolved mysteries in the field of astrophysics. To unravel the secrets of these cosmic shadows is to delve into the fundamental building blocks of the universe, to explore the very forces that govern the structure and evolution of the cosmos. It is a journey that has captivated the minds of scientists and philosophers alike, as they strive to understand the nature of reality and our place within it. At the core of the mystery surrounding the composition of the universe lies the elusive substance known as dark matter. This invisible and undetectable component of the cosmos is believed to make up around 85% of the total mass of the universe, acting as a vast, unseen scaffolding that supports the visible structures we observe, from the smallest galaxies to the largest clusters of galaxies. The first hints of dark matter's existence came in the 1930s, when the Swiss astronomer Fritz Zwicky noticed that the galaxies within the Coma cluster were moving much faster than expected, based on the visible mass of the cluster. This suggested that there must be an additional unseen source of gravitational influence holding the cluster together, a revelation that would later lead to the concept of dark matter. Since Zwicky's initial observations, the evidence for dark matter has only grown stronger. Measurements of the rotation of galaxies, the gravitational lensing of light by galaxy clusters, and the cosmic microwave background radiation all point to the existence of this mysterious substance that permeates the universe, exerting a powerful influence on the formation and evolution of cosmic structures. But what exactly is dark matter? Despite decades of intense study and investigation, the true nature of this elusive component of the cosmos remains one of the greatest unsolved mysteries in modern science. Numerous theories and hypotheses have been proposed, ranging from exotic subatomic particles to modifications of our understanding of gravity. But as of yet, no definitive answer has emerged. One of the leading theories is that dark matter is composed of a new type of fundamental particle, known as a WANP, weakly interacting massive particle. These hypothetical particles would interact with ordinary matter primarily through the weak nuclear force, making them incredibly difficult to detect with current technology. Countless experiments around the world are searching for these WIMPs, but so far their efforts have been frustratingly inconclusive. Alternatively, some scientists have proposed that the observed effects attributed to dark matter may be the result of a more fundamental breakdown in our understanding of gravity, rather than the presence of an unknown substance. These modified gravity theories, while intriguing, have yet to gain widespread acceptance within the scientific community, as they struggle to account for the wealth of observational evidence that points to the existence of dark matter. Regardless of the ultimate nature of dark matter, one thing is clear. This invisible component of the universe has played a crucial role in shaping the structures we observe today. The gravitational influence of dark matter is believed to have been the driving force behind the formation of the first galaxies, acting as a scaffolding upon which the visible matter could condense and coalesce. Without dark matter, the universe would have looked vastly different, a more diffuse and homogeneous collection of matter, with far fewer of the intricate structures that we associate with the cosmos. It is the unseen gravitational pull of dark matter that has guided the formation and evolution of galaxies, clusters, and the vast, interconnected web of filaments that make up the large-scale structure of the universe. As scientists continue to investigate the nature of dark matter, they are not only seeking to unlock the secrets of this mysterious component of the cosmos, but also to gain a deeper understanding of the fundamental forces that govern the universe as a whole. The quest to unravel the mysteries of dark matter is a testament to the boundless human curiosity that has driven scientific exploration for centuries, and it promises to yield profound insights into the very fabric of existence. While dark matter has captured the attention of cosmologists for decades, an even more perplexing and enigmatic component of the universe has emerged in recent years: the mysterious force known as dark energy. This unseen and largely unexplained influence is believed to make up the majority of the total energy content of the universe, accounting for over 60% of the cosmos, and it is playing a crucial role in shaping the future of the universe itself. The discovery of dark energy came in the late 1990s, when observations of distant supernova revealed that the expansion of the universe was not slowing down, as had long been assumed, but rather was accelerating. This unexpected revelation, which earned the Nobel Prize in Physics in 2011, challenged the prevailing models of cosmology and forced scientists to rethink their understanding of the fundamental nature of the universe. According to the current models of cosmology, this accelerating expansion is being driven by an unknown form of energy that is inherent to the very fabric of space-time itself. This dark energy, as it has come to be known, is thought to exert a repulsive anti-gravitational force that is counteracting the attractive force of gravity, causing the universe to expand at an ever-increasing rate. But the true nature of dark energy remains one of the greatest mysteries in modern physics. Unlike dark matter, which is believed to be composed of some form of as yet undiscovered particle, dark energy is thought to be a property of space itself, a fundamental characteristic of the universe that is encoded into the very laws of nature. One of the leading theories is that dark energy is the result of the vacuum energy, or the zero-point energy, of the quantum fields that permeate the universe. According to the principles of quantum mechanics, even in the absence of any particles or matter, there is a constant background energy that exists in the vacuum of space. This vacuum energy, which is predicted by the equations of quantum field theory, is thought to be the source of the repulsive force that is driving the accelerating expansion of the universe. Alternatively, some scientists have proposed that dark energy may be the result of a modification or extension of our current theories of gravity, rather than a new form of energy per se. These modified gravity theories, while intriguing, have yet to gain widespread acceptance as they struggle to account for the wealth of observational data that points to the existence of dark energy. Regardless of its ultimate nature, the impact of dark energy on the future of the universe is profound. According to the current models, the accelerating expansion driven by dark energy will eventually lead to a future in which the universe becomes increasingly cold, diffuse, and devoid of structure. As the distance between galaxies continues to grow, the night sky will eventually go dark, and the cosmos will enter a state of eternal, accelerating expansion. This stark vision of the universe's future stands in stark contrast to the prevailing models of the past, which had envisioned a universe that would eventually collapse back in on itself in a big crunch. Instead, the influence of dark energy appears to be pulling the universe apart, leading to a future that is vastly different from anything we have ever known. The discovery of dark energy has not only transformed our understanding of the universe's past and present, but it has also forced us to confront the profound implications of the cosmos' ultimate fate. As we continue to unravel the mysteries of this enigmatic force, we are sure to gain deeper insights into the fundamental nature of reality and the role that unseen components like dark energy play in shaping the grand cosmic drama that unfolds around us. While dark matter and dark energy are often discussed as separate and distinct components of the universe, the reality is that these two mysterious forces are inextricably linked, working in concert to shape the structure and evolution of the cosmos on the grandest scales. At the heart of this interplay is the delicate balance between the gravitational influence of dark matter and the repulsive anti-gravitational force of dark energy. On the one hand, dark matter serves as the scaffolding upon which the visible structures of the universe, galaxies, galaxy clusters, and the vast, interconnected web of filaments are built. The gravitational pull of dark matter has been the driving force behind the formation and growth of these cosmic structures, acting as the invisible glue that holds them together. On the other hand, dark energy, with its pervasive and ever-increasing influence, is working to counteract the attractive force of gravity, driving the universe's expansion at an accelerating rate. This expansion, in turn, is working to weaken the gravitational influence of dark matter, reducing its ability to shape the large-scale structures of the cosmos. The delicate balance between these two unseen components of the universe has had a profound impact on the evolution of the cosmos, from the earliest moments after the Big Bang to the present day and into the distant future. In the early universe, the dominance of dark matter was crucial in the formation of the first galaxies and the large-scale structures we observe today. But as dark energy has grown in influence, it has begun to shape the future of the universe, driving the accelerating expansion that will eventually lead to a cold, diffuse, and increasingly isolated cosmos. Moreover, the interplay between dark matter and dark energy is not only shaping the large-scale structures of the universe, but it is also having a profound impact on the evolution of individual galaxies and their constituent stars. The gravitational influence of dark matter, for example, is believed to be crucial in determining the formation and distribution of stars within a galaxy, while the expansionary force of dark energy is thought to be responsible for the eventual dissolution of these galactic structures over cosmic timescales. As scientists continue to investigate the mysteries of dark matter and dark energy, they are not only seeking to unlock the secrets of these unseen components of the universe, but also to gain a deeper understanding of the fundamental forces that govern the cosmos as a whole. The quest to unravel the interplay between these two enigmatic entities is a testament to the boundless human curiosity that has driven scientific exploration for centuries, and it promises to yield profound insights into the very fabric of existence. As we gaze out into the vast expanse of the cosmos, it is clear that the visible universe we observe is but a mere fraction of the true nature of reality. Underlying the familiar structures of galaxies, stars, and planets lies an unseen and mysterious realm, a hidden component of the universe that has eluded our understanding for decades, yet exerts a profound influence on the very fabric of existence. This hidden realm is the domain of dark matter and dark energy, two of the most perplexing and enigmatic concepts in modern cosmology. Together, these mysterious entities make up the vast majority of the universe, accounting for over 95% of the total mass and energy that shapes the cosmos we inhabit. And yet, despite their overwhelming dominance, the true nature of dark matter and dark energy remains one of the greatest unsolved mysteries in the field of astrophysics. As scientists continue to investigate these unseen components of the universe, they are not only seeking to unlock the secrets of dark matter and dark energy, but also to gain a deeper understanding of the fundamental forces that govern the cosmos as a whole. The quest to unravel the mysteries of the unseen universe is a testament to the boundless human curiosity that has driven scientific exploration for centuries, and it promises to yield profound insights into the very fabric of existence. From the search for exotic subatomic particles that may make up the elusive dark matter, to the ongoing efforts to reconcile the observed effects of dark energy with our current theories of gravity, the path forward is paved with both challenges and opportunities. And as we continue to push the boundaries of our knowledge, new and unexpected discoveries are sure to arise, further transforming our understanding of the universe and our place within it. Indeed, the exploration of the unseen universe is not merely a scientific endeavor, but a philosophical and existential journey as well. The very existence of dark matter and dark energy, these invisible components that dominate the cosmos, challenges our most fundamental notions of reality, causality, and the nature of existence itself. As we unravel these mysteries, we may be forced to confront the limitations of our understanding and the possibility of a reality that extends far beyond the confines of our own observations and experiences. Yet, this challenge is precisely what makes the study of dark matter and dark energy so captivating and essential. For in seeking to unlock the secrets of the unseen universe, we are not only expanding the boundaries of our scientific knowledge, but also confronting the very nature of our own existence and the place of humanity within the grand cosmic drama. It is a journey of discovery that promises to transform our understanding of the universe and our place within it, and one that will undoubtedly continue to captivate and inspire generations of scientists and thinkers to come. When we look out at the cosmos, what we see is only a small part of the complete picture. The stars, planets, and galaxies that populate the night sky make up less than 5% of all the matter and energy that exist in the entire universe. The rest is made up of strange, invisible substances that we call dark matter and dark energy. For decades, astronomers have been gathering evidence that these dark components are the dominant themes shaping the growth and behavior of structures throughout the universe. But exactly what dark matter and dark energy are remains one of the most perplexing mysteries in all of modern physics. Let's start with what we can observe directly. When astronomers look out into the heavens and analyze the light coming from galaxies, they can see bright collections of stars loosely bound together by gravity. By carefully tracking the movement of stars within galaxies, scientists have determined how much visible mass is actually present based on the star's orbital speeds. But here is where things get strange. The orbital speeds detected do not match what is actually expected based on just the visible stars and gas that emit light. Stars at the outer edges of galaxies are moving much faster than what would be predicted by the gravitational pull exerted by just the luminous matter we can see. In fact, they are going about twice as fast as the luminous matter alone could account for. This discrepancy was first noticed in the 1970s when astronomer Vera Rubin made detailed observations of galactic rotation curves. The only way the behavior of these stellar orbits could be explained was if galaxies contain a much larger amount of surrounding dark matter that we cannot see. This unseen material has its own gravity, that is helping to keep the stars zooming along at such high speeds, even far away from the central bulge of glowing stars. Gravity is the only force powerful enough to force things to move so quickly while acting over such vast distances. But dark matter is not just affecting galaxies. Its presence can also be observed on even larger cosmic scales through its gravitational lensing effects. When huge galaxy clusters pass between us and more distant galaxies, the light from those background objects gets bent and distorted slightly as it travels towards our telescopes. This is a prediction of Einstein's general theory of relativity, where gravity warps and affects the paths of light rays. The amount and pattern of gravitational lensing detected from massive clusters cannot be explained by the visible stars and hot cluster gas alone. Dark matter's extra gravity is needed to generate the observed lensing patterns, as it acts to magnify background galaxies and even split their light into multiple distorted images. Through careful studies of the cosmic microwave background radiation left over from the early universe, we have another clue about dark matter's importance. Tiny temperature fluctuations in this primordial microwave glow betray the seeds of structure that would later grow into the galaxies and clusters we see today. The patterns and sizes of these early inhomogeneities match predictions from theoretical models only if the universe contains a significant amount of cold dark matter to help light up these fluctuations and drive structure formation following the Big Bang. Ordinary baryonic matter alone does not seem to provide enough gravitational scaffolding to account for the assembly of all cosmic structure in the time available. Taken all together, the different and diverse pieces of astronomical evidence point strongly to a conclusion that over 80% of all matter in the universe is composed of this mysterious dark matter. It is spread throughout galaxies and galaxy clusters, as well as existing in the vast voids between cosmic structures. Wherever scientists look, they find need for more matter than what emits light. The glow of stars and galaxies is just the tip of the iceberg when it comes to the material that makes up our universe. So while we have compelling evidence that dark matter exists, the biggest puzzle remains. Exactly what is it? Despite making up most of the matter density of the cosmos, dark matter does not interact with light or any other type of electromagnetic radiation that we can detect. It passes right through normal baryonic matter like stars and gas without collisions. So astronomers cannot study it directly through telescopes as we can see galaxies. Dark matter reveals itself only through its gravitational interactions on huge cosmic scales. The most popular theoretical candidates proposed to explain dark matter's properties come from the realm of particle physics. One idea is that dark matter could consist of as yet undetected subatomic particles left over from the very early universe, prior to the formation of the first stars and galaxies. These hypothetical weakly interacting massive particles, or WIMPs, would interact via gravity and the weak nuclear force, but not electromagnetically. WIMPs are a common prediction from extensions to the standard model of particle physics, like supersymmetry and extra-dimensional theories. If they exist, WIMPs would pass through the Earth and atmosphere without friction, making them perfect dark matter. Another possibility is that dark matter could be composed of lighter particles called actions. Originally conceived to solve puzzling behaviors of fundamental forces, actions would have been copiously produced in the early universe and could still remain today as a cold dark matter candidate. Actions would interact even more weakly than WIMPs, potentially making them difficult to definitively detect. But both WIMPs and actions remain theoretical. After decades of effort, we still lack a confirmed detection of any hypothetical dark matter particle. To truly learn what dark matter consists of, astronomers and physicists are pursuing both indirect and direct detection strategies. Indirect searches look for potential evidence of dark matter particles annihilating or decaying into normal matter that can be detected. For example, observations of gamma rays from galaxy clusters and galaxy centers hoped to reveal the signature imprint of WAMP annihilation byproducts like electrons and positrons. Meanwhile, terrestrial dark matter detection experiments operate deep underground and employ sophisticated techniques to directly discover and analyze potential WAMP interactions in specially designed particle detectors. If any dark matter particles interact in the detectors, scientists could learn their mass, interaction strengths, and help point to the underlying particle physics theory, explaining the cosmological dark matter's origin. The direct detection field is an amazingly active area of research right now given dark matter's importance across astronomy and physics. Some projects home in on potential WAMP nucleus recoils using liquid noble gas like xenon as the target medium, while others hunt for phonon signals in ultra-pure crystals caused by WAMP scatters. And there are also experiments sensitive to the hypothetical axion particle by searching for signatures of actions converting into photons in the presence of powerful magnetic fields. Though detecting dark matter directly is technically difficult given its weakness of interaction, new experiments are pushing sensitivity barriers lower each year with even larger and more advanced detector technologies. So in summary, while dark matter has established itself as the dominant invisible component shaping galaxies based on its gravitational effects, identifying exactly what it is made of remains one of our biggest unsolved problems. Current astronomical observations point strongly to new fundamental physics beyond the standard model at work. By converging insights from cosmological prose, particle physics ideas, and dedicated search experiments, scientists hope to soon pin down dark matter's true identity and nature. With so many exciting efforts underway, the coming years promise great potential breakthroughs that could revolutionize our understanding of physics and the hidden majority of reality driving the structure and evolution of the entire cosmos. One of the earliest and most compelling pieces of observational evidence supporting the existence of dark matter came from analyzing the rotation speeds of stars and gas clouds in galaxies beyond our own Milky Way. As astronomers developed more powerful telescopes and refined spectroscopy techniques throughout the 20th century, they began mapping out the detailed rotational motions within other island universes, as galaxies were then known. Careful tracking of the orbital speeds of individual stars and clouds of luminous gas allowed for constructing the first galactic rotation curves, plots showing how orbital velocity changes as a function of distance from the galaxy's center. The results came as a major surprise to theorists. Galaxy formation models at the time were based on the then dominating view that galaxies were composed nearly entirely of visible stars and gas. According to Newtonian physics and the laws of orbital motion, the outermost stars in a galaxy should move slower than interior ones closer to the dense central bulge of luminous mass. As distance increases from the hub of a galaxy, where most shining stars aggregate, the strength of gravitational pull diminishes, so orbital speeds should taper off progressively. In a normal stellar system residing in apparent equilibrium, stars closer to the center feel a stronger gravitational tug than those further away circling the edges. So when astronomer Vera Rubin obtained the first precise rotation curves for other galaxies, like our Milky Way's Andromeda neighbor in the 1970s, her results flew in the face of expectations. Far from tapering off at the boundaries of galaxy disks, as theory predicted, the plotted orbital velocities remained perfectly flat, not changing at all even out to the last measured gas clouds and stars. In other words, objects located far from the visible center of galaxies move just as swiftly as those nearer in, against all classical wisdom that orbital speeds should decrease away from a gravitating mass. Something was clearly amiss. For velocities to stay constant instead of falling with distance could only be possible if galaxies contained far more mass than what emitted visible light from shining stars. In fact, Rubin found inner rotation speeds matched predictions from only about 10% of the total luminous matter present. The outer regions showed rotational velocities indicating at least 5 to 10 times more gravitating mass than accounted for by the optically visible disk alone. Only the presence of huge amounts of some unseen, dark form of matter permeating galaxies could hold onto stars at their observed blazing speeds several times what gravity from normal stars and gas warranted. Rubin's work swiftly became the first compelling observational proof that the bulk of galactic mass did not shine at all. Most of any galaxy must actually be composed of some unknown, dark substance we cannot directly detect. Its gravity is the only explanation consistent with the unexpected flatness of observed rotation curves extending far from the optical center. Dark matter had to vastly outweigh the visible stars and gas clouds we can observe with telescopes. Otherwise, orbital velocities would drop at increasing radii. Further observations not only confirmed Rubin's original results for our own Milky Way and neighboring spiral Andromeda galaxy, but also revealed this anomalously high dark matter content to be a universal phenomenon applying to all galaxies, no matter the type, spiral, elliptical, or irregular. The rotation curves of all galaxies exhibit the same telling signature of declining visible mass compared to rising total needed to explain orbital motions. The presence of some unseen, weakly interacting form of matter has to dominate galaxy halos in order to claim onto stars zipping around fringes at precisely measured speeds. Since Rubin's initial findings, astronomers have gathered rotation curve measurements for thousands of galaxies. Advances in digital detectors, multi-object spectroscopy, and space-based observatories like the Hubble Space Telescope have greatly facilitated collecting ever larger samples, and the data consistently emphasizes how normal this excess mass discrepancy is throughout the observable universe. Studies of galaxies across wide ranges of distances find that at radii beyond the main optical disks, rotation velocities asymptotically level off to approximately constant speeds, indicating galaxy masses many times higher than visible light can account for. Furthermore, subsequent work combining both emission line measurements of hydrogen gas with absorption line spectroscopy of individual stars has improved mapping detail within galactic rotation curves. Not only have orbital velocities been plotted with increasing precision to larger radii, but the results continue signaling well past where visible mass ought to taper off sharply according to theory. Even at distances of several times an optical radius, outskirts show no decline in rotational support from the mysterious dark material outweighing normal stars. Its gravity remains strong enough to hold galactic fringes together, moving at hundreds of kilometers per second. Another important advance came with using infrared surveys to trace the actual distribution of older stellar populations lost in visible wavelengths. While young hot stars dominate the light we see in familiar galaxy photographs, the bulk of a galaxy's mass is overwhelmingly locked up in hard-to-detect faint stars nearing the ends of their lifetimes. Masses from infrared tracers like Red Giant Branch and main sequence turn-off stars more accurately gauge the true distribution of regular baryonic material alone, and infrared rotation curves agree with visible results. The outskirts still rotate too swiftly for ordinary mass concentrations. When the expected tapering off based on the actual luminous profiles fails to materialize, this rules out possible modifications to standard gravity able to reproduce flat observed curves. The only viable explanation left is attributing the missing mass deficit to dark matter dominating the extended galactic halo regions. Its presence provides that continuous volumetric pull holding together the far-flung material keeping rotation speed steady over vast empty spaces between the visible disks. Tweaking our understanding of inertia or gravitation simply does not rescue galaxy formation without resorting to something unseen clinching orbital motions. Moreover, multi-wavelength studies encompassing visible, infrared, radio, and microwave views of galaxies demonstrate how the dark matter overwhelmingly prevails through different tracers. Mass models fitted to all emitted light converge smoothly onto the same declining luminosity, but persisting total mass profiles beyond visible edges as dark matter takes over dynamically. This continuity between observational windows further bolsters that the discrepancy has a true astrophysical origin in gravitating non-emitting material rather than unknown systematics in astronomy. Perhaps the strongest confirmation comes from kinematic studies of gas giant galaxies like our own. With multiple orbits of molecular clouds and giant dissociations of young stars mapped across immense radial and angular distances, the Milky Way's rotation curve emerges as ideally suited to pin down its mass distribution. Remarkably, even at galactocentric radii over 100,000 light-years beyond Earth, where visible stars thin out, gas motions imply precisely constant rotation akin to nearby galaxies. Milky Way studies using myriad tracers all arrive at the inescapable verdict. The majority of our galaxy's mass consists of invisible material whose gravity holds it intact at the outskirts. Overall, the copious data amassed from galactic rotation curves across the decades amounts to overwhelming observational evidence that dark matter is the dominant component of galaxies. Normal stars and gas emit light, but fail to account for the observations dynamically. Only through a pervasive, diffused halo of non-radiating material can the orbital speeds persist outside visible boundaries. In fact, the coherence between measurements from a multitude of galaxies of all types using diverse observational methods to trace their motions underscores how the rotation curve phenomenon points squarely at dark matter's prevalence. This profoundly altered our conception of galaxies' internal workings and helped herald the rise of the cold dark matter paradigm, guiding modern cosmological theory. So while the exact identity and particle nature of dark matter remains to be determined, its gravitational effects through rotation curve measurements comprise one of astronomy's strongest empirical pillars. Over half a century since Vera Rubin's pioneering work, galactic dynamics continue bearing out its dominance through a wealth of observational details. Though invisible, dark matter's impact dramatically shapes how galaxies form and evolve according to its measured gravitational fingerprints within their growth. Untangling dark matter's deeper properties relies on both new generations of observational facilities as well as theoretical advances linking its particle origins to high-energy physics, two frontiers that hold immense promise to finally uncover dark matter's long-concealed but dominant presence throughout cosmic history. While dark matter's gravitational effects have established its cosmological importance, unlocking its deeper identity remains an immense experimental and theoretical challenge. Despite comprising the majority of all matter in the universe, dark matter interacts so feebly that it passes through normal matter without collisions and does not emit or absorb light. Its invisible interactions and lack of electromagnetic signature mean dark matter remains completely undetected so far by astronomical observations alone. To determine what type of particle might account for dark matter's gravitational behavior, scientists must turn to ideas from fundamental physics, especially the realm of particle theory, which seeks to describe dynamics on the smallest subatomic scales. One of the leading frameworks for particles and forces beyond the standard model of particle physics is supersymmetry, or SUSY for short. This theory proposes each known particle as a massive superpartner that differs by a half unit of intrinsic spin, but is otherwise similar. For example, electrons would have superpartners called selectrons, quarks would partner with squarks, and so on for all known particles. If SUSY is valid at the TeV energy scales accessible with the Large Hadron Collider, it provides an elegant solution to the hierarchy problem, balancing quantum effects with observed particle masses. SUSY also allows for the lightest supersymmetric particle, or LSP, that could serve as an ideal cold dark matter candidate. Many SUSY models predict the LSP will be the neutralino. a stable, electrically neutral combination of supersymmetric partners to fundamental standard model particles. As a Majorana fermion with no electric charge or strong interactions, the neutralino would rarely scatter or interact with normal matter, making it survive abundantly since the Big Bang. Yet its mass of around 100 GeV to a few TeV places it firmly within the realm of experimental accessibility. Intriguingly, neutralinos as weakly interacting massive particles, WIMPs, fit all criteria needed to explain dark matter. They were produced thermally in early universe conditions, account for the observed cosmological density through self-annihilation freeze-out, and have weakness of interaction allowing them to cluster gravitationally without conflicting with direct detection experiments so far. Should supersymmetry prove relevant at the TeV scale accessible with collidors like the LHC, discovering the predicted plethora of superpartners would lend strong credence to the neutralino dark matter hypothesis. Interactions observed between stable supersymmetric states may reveal the specific SU-SLI breaking mechanism at work and help narrow model building. The Large Hadron Collider colliding protons at phenomenal energies provides humanity's best bet for synthesizing SU-SLI particles if they exist at masses up to several TeV. So far, while SU-SI remains a leading idea, no clear signs have emerged in early LHC data. But with more collision runs at higher luminosities still ahead, the LHC may finally detect superpartners hinting at a particle identity for dark matter. Another compelling theoretical idea proposes dark matter composed of actions, subatomic entities arising from a proposed extension to the quantum chromodynamics sector of the Standard Model. Originally introduced to resolve the strong CP problem of why the universe preserves charge parity symmetry, QCD actions turn out to potentially yield the observed cold dark matter abundance today through non-thermal production. They are a form of fuzzy cold dark matter with extraordinarily weak interactions mediated by a new axion field. Crucially, axions could be very light entities with masses ranging from about microwave to perhaps a few MeV, depending on model parameters. Such an ultralight particle is cold by virtue of its low de Broglie wavelength larger than astrophysical scales. Remarkably, axion masses in this range mean they may have contributions to the matter density similar to the observed value inferred from the CMB and gravitational structure growth. So axions hold promise as a dark matter candidate fulfilling a similar particle physics motivation, as well as accounting for cosmology through a unique formation scenario. Both theoretically and observationally, significant effort targets detecting or ruling out axion dark matter candidates. On particle physics fronts, experiments like ADMX employ resonant microwave cavity techniques, hoping to convert axions into detectable photons in strong magnetic fields. ADMX is currently sensitive to axions in the 10 to 25 microwave mass band, while next-generation detectors like CULT-ASK aim even lower. Other approaches rely on neutron stars or black hole superradiance effects to probe astrophysical signatures across wide regions of axion parameter space. Resonant axions may also show up in precision cosmological datasets, requiring computation of axion effects in the early universe. Theorists continue refining axion formation scenarios and couplings as well to keep experimental and observational searches optimally focused. While WIMPs and axions exemplify compelling dark matter particle candidates from physics beyond the Standard Model, other alternatives also exist and warrant exploration. For example, sterile neutrinos, right-handed counterparts to known active neutrinos, could potentially provide dark matter candidates around the keV mass scale if mixing with active neutrinos. Their Fermi ball distribution may manifest distinctively through keV scale X-ray lines from two-body decays discovered by future X-ray telescopes. Another candidate arises from theories embedding our familiar universe within brain world scenarios. In these models, only gravity leaks into extra dimensions, while standard model particles are confined to a three-dimensional brane. It's possible for hypothetical brane fluctuations called Brownians to emerge contributing dark matter in Earth's vicinity around 1 TeV, and primordial black holes present another speculation, where black holes may have seeded from primordial density fluctuations and comprise dark matter below 100 solar masses. Each potential opens additional research avenues to test through particle physics, astrophysics, and precision cosmological measurements. Overall, the variety of well-motivated particle candidates proposed to date suggests dark matter emerges from new physics principles beyond our current standard model understanding of particle interactions and forces. Even if one candidate like the neutralino or QCD axion proves correct, discovering dark matter's identity will illuminate profound new facets of fundamental theory and microcosmic particle properties. Its gravitational effects provide indispensable macroscopic evidence driving experimental and theoretical detection strategies across many complementary fields seeking the crucial next breakthrough. With increasing sensitivity probing deeper into prediction ranges for WIMPs, actions, and other candidates, the coming years hold tremendous promise to finally reveal what invisible material has shaped cosmic evolution since the early universe. One of the most unexpected astronomical revelations of the past century came with the serendipitous discovery that the observable cosmos is not only expanding following the Big Bang, but that this expansion is actually speeding up over time. Determining the precise rate at which the universe stretches apart holds profound implications for cosmology, yet prior measurements in the late 20th century found expansion to be steadily slowing due to gravity. What could be responsible for propelling galaxies apart at an ever swifter pace, defying ordinary expectations? The surprising culprit came to be known as dark energy, and unlocking its deeper nature stands as one of the foremost questions in both astrophysics and particle physics today. A crucial breakthrough came in the 1990s thanks to ambitious efforts to map distant supernovae, the titanic explosions of massive stars at the ends of their lives. By analyzing characteristic brightness variations in Type Ia supernovae, which can be treated as reliable standard candles due to shared ignition and detonation mechanisms, astronomers developed a powerful toolkit for gauging huge cosmological distances that provided a direct way to watch the expansion history unfold over time. Two independent teams led by Saul Perlmutter and Brian Schmidt employed specially designed wide-field cameras on large ground-based telescopes to painstakingly survey and monitor over 50 Type Ia supernovae located billions of light-years away, representing locusts far back in time. What they found shocked the cosmology community. Rather than dimming slightly with increasing distance as expected from a cosmology where normal matter and radiation were slow in expansion via gravity, the most distant supernova appeared surprisingly fainter than forecast. This implied they lay not merely billions of light-years from Earth, but slightly farther than simple extrapolation of a decelerating expansion would place them given their observed redshifts. Only one scenario could accommodate this anomalous observation: that the universe's stretching has been accelerating ever faster as time proceeds, literally outpacing the rate of change predicted by known matter and force compositions. Dark energy's mysterious anti-gravity force had to dominate, accelerating galaxies away from each other more powerfully than ordinary mass can hold them together. Follow-up studies cementing these momentous findings included analyzing supernova at even greater distances across wider patches of sky, refining systematic uncertainties, and obtaining independent confirmations through alternative techniques like cosmic microwave background measurements, baryon acoustic oscillations, and cluster counts utilizing galaxies' spatial distributions. Both the amplitude and uniformity of the acceleration signal proved robust against potential systematic errors or statistical fluke. Today, dozens of studies employing diverse cosmological probes all consistently point toward the inescapable conclusion that around 70% of all cosmic energy resides in some mysterious dark energy accelerating universal expansion. The cosmological constant Einstein introduced to balance general relativity now arises as the simplest candidate description, though pinning down its deeper physical nature remains elusive. Einstein originally conceived the cosmological constant as a modification to general relativity tying into empty space itself, giving rise to a small positive vacuum energy density. Setting its value to zero left general relativity, agnostic about cosmic expansion or curvature. Decades later, when expansion first emerged observationally, Einstein called omitting the constant his biggest blunder, as it could have anticipated Hubble's discovery. Dark energy's modern reinterpretation as an innate energy of empty space is tantalizing, yet quantum field theory at present predicts a much larger cosmological constant value than observed, due to vacuum fluctuations from known elementary particles. Reconciling quantum gravity with observations requires new physics beyond the standard model to stably fine-tune its value enormously lower. Perhaps dark energy is not fundamental like Einstein's constant, but instead arises in alternative theories extending general relativity on immense cosmological scales. Modifications letting acceleration emerge without a cosmological constant invoke notions like extraspatial dimensions, dynamical scalar fields, or quantum gravitational effects tied to cosmic event horizons. While challenging to test directly, such proposals aim to naturally generate cosmic acceleration at today's epoch from high-energy principles. Other speculations look to observational questions around dark energy's possible time variation or spatial clustering that emergence within our local part of the multiverse might address. Regardless of nature, dark energy's tiny density remains one of the most pressing problems for theoretical physics today. Understanding its origin promises transformative implications for fundamental physical laws across microscopic and astrophysical realms. Confronting dark energy on the grandest scales motivates cutting-edge observational facilities capable of precisely mapping expansion history while probing potential time variations. Projects like the Dark Energy Survey, Large Synoptic Survey Telescope, Euclid spacecraft, and Wide Field Infrared Survey Telescope will amass huge catalogs of galaxies and galaxy clusters to constrain expansion history and growth of structure through baryon acoustic oscillations, weak gravitational lensing, galaxy cluster counts, and other unique signatures. Space missions like the WFIRST Infrared Telescope aim to leverage distant supernova into the far cosmic past to better disentangle dark energy behavior. Complementary probes utilize phenomena as diverse as strong gravitational lenses, Lyman alpha forest absorption, and the intrinsic alignments of galaxy shapes to probe dark energy's impacts on structure formation. Meanwhile, ambitious stage IV ground-based experiments envisioned for the next decade include technologies like electromagnetic optical infrared interferometry to directly image exoplanets, as well as the supermassive black holes powering quasars across cosmic history, relating their distributions to dark energy. At smaller scales, laboratory experiments probe quantum coherence for certain modified gravity models, potentially detectable through precision atom interferometry. Particle physics may offer clues through searches for new ultralight fields detectable at colliders or indirectly through astrophysical means. The worldwide effort to pin down dark energy demonstrates powerful synergies between instrumentation at the cutting edge of physics discovery, together with advances in theoretical models of fundamental constituents and forces governing our expanding universe. In closing, dark energy's revelation that cosmic expansion is accelerating marks one of the landmark scientific discoveries of modern times. While we may not yet understand its underlying cause, observations across cosmological probes have firmly established dark energy's reality and importance for shaping cosmic evolution. Its gravitationally repulsive properties provocatively point to physics beyond Einstein's theory or our current grasp. Unlocking the origin and behavior of dark energy stands as one of the foremost challenges at the interface of theoretical cosmology, astrophysics, and particle physics alike. With ambitious research across these fields ongoing, including next-generation experiments to precisely map expansion history and chase the faintest signatures predicted by theoretical models, the next decade promises revolutionary insights that may finally unveil the deepest nature of this ubiquitous yet enigmatic component dominating the universe on its grandest scales. In the vast, darkened tapestry of the cosmos, there exists a phenomenon so profound, so captivating, and so enigmatic that it has long captured the imagination of scientists and the general public alike: the black hole. These celestial titans, regions of space-time so intensely gravitationally bound that not even light can escape their clutches, are among the most remarkable and mysterious objects in the universe, serving as gateways to the unknown and challenging our very understanding of the fundamental laws of physics. Black holes, once mere theoretical constructs predicted by the groundbreaking work of Albert Einstein, have since been observed and studied in meticulous detail, revealing a wealth of insights into the nature of gravity, the evolution of stars, and the underlying structure of the universe itself. From the supermassive black holes that lurk at the hearts of most galaxies to the stellar mass black holes formed by the collapse of massive stars, these cosmic behemoths have become central to our understanding of the cosmos and the forces that govern its endless complexity. Yet, despite the wealth of knowledge we have gained about black holes, they remain shrouded in mystery, their true nature and behavior continuing to defy our efforts to fully comprehend them. What lies at the heart of a black hole? How do these enigmatic entities form, and what role do they play in the larger cosmic tapestry? These are the questions that have captivated generations of scientists, driving them to explore the boundaries of our understanding and to push the limits of human knowledge. To delve into the study of black holes is to embark on a journey of discovery that promises to yield profound insights into the very fabric of reality. It is a quest to unravel the deepest secrets of the universe, to peer into the abyss, and to confront the limits of our own comprehension. And as we continue to unlock the mysteries of these cosmic titans, we are sure to be transformed by the knowledge we gain, forever altering our perception of the world around us. The story of black holes begins, as do many cosmic tales, with the remarkable life and death of stars. For it is in the final, cataclysmic stages of a star's existence that the conditions necessary for the formation of a black hole are set in motion, as the immense gravitational forces within the stellar interior overcome the outward pressure of nuclear fusion and cause the star to collapse in on itself. The exact process by which a star becomes a black hole is a complex and dynamic one, shaped by the interplay of the fundamental forces of nature and the unique circumstances of each individual stellar system. But at its core, the formation of a black hole is the result of a star's mass exceeding a critical threshold, known as the Chandrasekhar limit, which defines the maximum mass a star can maintain before it can no longer support itself against its own gravitational pull. For the vast majority of stars, the end of their lives comes in the form of a supernova explosion, where the star's outer layers are ejected into the surrounding space, while the core collapses down to form an incredibly dense object known as a neutron star. But for the most massive of stars, those with masses several times greater than that of our own Sun, the gravitational forces at play are simply too great to be counteracted by the outward pressure of nuclear fusion. As these massive stars exhaust their fuel and their cores begin to collapse, the immense gravitational forces at work overcome all other forces, causing the star to undergo a catastrophic implosion. The matter that once made up the star is compressed down to a single, infinitely dense point known as a singularity, a region where the very laws of physics as we understand them break down. This singularity, surrounded by an event horizon, a point of no return beyond which nothing, not even light, can escape, is the defining feature of a black hole. It is a region of such intense gravitational pull that it warps and distorts the very fabric of space-time, creating a cosmic anomaly that challenges our most fundamental notions of reality. But the formation of black holes is not limited to the collapse of individual stars. At the heart of most, if not all, galaxies lies a supermassive black hole, a colossal gravitational behemoth that can have a mass millions or even billions of times greater than that of our Sun. These supermassive black holes, which are thought to have formed in the earliest epochs of the universe, have played a crucial role in shaping the structure and evolution of the galaxies they inhabit, their immense gravitational influence guiding the motions of stars, gas, and dust within their galactic domains. The formation of these supermassive black holes is a topic of intense scientific inquiry, with numerous theories and hypotheses proposed to explain their origins. Some suggest that they may have formed from the mergers of smaller black holes in the early universe, while others posit that they may have arisen from the collapse of massive, primordial gas clouds that existed in the wake of the Big Bang. Regardless of their precise origins, the presence of these colossal black holes at the centers of galaxies has had a profound impact on the cosmic landscape, shaping the very structure and evolution of the universe itself. Their gravitational influence has been a driving force behind the formation and growth of galaxies, and their interactions with the surrounding matter and energy have given rise to some of the most spectacular and enigmatic phenomena observed in the cosmos. As captivating and intriguing as the formation of black holes may be, it is their remarkable properties and the challenges they pose to our understanding of the universe that truly capture the imagination. For within the event horizon of a black hole, the very laws of physics as we know them break down, and we are confronted with the limits of our comprehension and the true nature of reality itself. At the heart of a black hole lies the singularity, a point of infinite density and curvature of space-time, where the classical laws of physics cease to apply. This singularity, a region where the very fabric of existence is stretched to its breaking point, is the ultimate embodiment of the unknown, a place where our understanding of the universe falters, and we are forced to confront the deepest mysteries of the cosmos. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape the grasp of the black hole's immense gravitational pull. This event horizon, a literal membrane separating the known from the unknown, is a testament to the power and influence of these cosmic behemoths, a reminder that there are limits to the universe that even our most advanced scientific theories cannot fully explain. But the properties of black holes extend far beyond the event horizon and the singularity at their cores. The intense gravitational forces that exist within a black hole have a profound effect on the very structure of space-time, warping and distorting the fabric of reality in ways that challenge our most fundamental notions of the universe. Within the event horizon, the normal rules of space and time no longer apply, as the intense gravitational fields stretch and compress the very dimensions of existence. Time itself appears to slow to a crawl, with the passage of seconds outside the black hole corresponding to years or even centuries within its grasp. And the curvature of space-time becomes so extreme that the very concepts of up and down or left and right lose all meaning, as the boundaries between the physical dimensions become blurred and indistinct. It is this profound and unsettling alteration of the very nature of reality that has made black holes such a captivating and enigmatic subject of scientific study. For in confronting the extreme conditions that exist within these cosmic anomalies, we are forced to confront the limits of our understanding and the possibility that the universe may operate according to principles that transcend our current models and theories. Indeed, the properties of black holes have led to the development of new and revolutionary concepts in physics, from the idea of spaghettification, the intense gravitational forces that would stretch a person crossing the event horizon into long, thin strands, to the concept of Hawking radiation, the thermal radiation emitted by black holes that could eventually lead to their evaporation. As we continue to study the remarkable properties of black holes and probe the boundaries of the unknown, we are sure to uncover even more secrets about the fundamental nature of the universe and the limits of our own comprehension. For these cosmic titans, with their ability to work the very fabric of existence, serve as gateways to the unknown, challenging us to expand the boundaries of our knowledge and to confront the mysteries that lie at the heart of the cosmos. While the properties of black holes themselves are captivating and enigmatic, it is their profound influence on the surrounding universe that truly underscores the remarkable and far-reaching impact of these cosmic behemoths. For black holes, be they the stellar mass variety, formed by the collapse of massive stars, or the supermassive giants that reside at the hearts of most galaxies, are not isolated entities, but rather play a crucial role in shaping the evolution and structure of the cosmos. At the most fundamental level, the intense gravitational fields of black holes have a significant impact on the motion and behavior of the matter and energy in their immediate vicinity. The powerful pull of a black hole can draw in and accrete surrounding gas, dust, and even entire stars, creating a swirling maelstrom of material that radiates incredible amounts of energy as it is drawn towards the event horizon. This accretion process, which can release vast quantities of electromagnetic radiation, high-energy particles, and even powerful jets of matter, is a testament to the immense influence of black holes on their local environments. The intense heat and radiation generated by the infalling material can ionize and excite the surrounding gas, creating spectacular active galactic nuclei, luminous, high-energy regions that can outshine the entire host galaxy. But the impact of black holes extends far beyond their immediate surroundings, as their gravitational influence can shape the structure and evolution of entire galaxies and cosmic structures. The supermassive black holes that reside at the centers of most galaxies, for example, are believed to play a crucial role in the growth and development of their host galaxies, their immense gravitational pull guiding the motions of stars, gas, and dust within the galactic disk. Indeed, the presence of a supermassive black hole at the heart of a galaxy appears to be a fundamental characteristic of galactic structure, with the mass of the black hole being closely correlated with the properties of the surrounding bulge and disk. This intimate relationship between black holes and their host galaxies has led to the development of theories suggesting that the growth and evolution of these cosmic titans are intimately linked, with the black hole's influence shaping the very structure and dynamics of the galaxy it inhabits. Beyond the realm of individual galaxies, the influence of black holes can also be seen in the formation and evolution of larger cosmic structures, such as galaxy clusters and the vast, interconnected web of filaments that make up the large-scale structure of the universe. The gravitational pull of black holes, both supermassive and stellar, can play a crucial role in the motions and interactions of these vast cosmic aggregations, with their influence shaping the distribution and properties of matter on the grandest scales. As we continue to study the impact of black holes on the surrounding universe, we are gaining invaluable insights into the fundamental processes that have guided the evolution of the cosmos. From the accretion of material and the generation of high-energy radiation to the shaping of galactic and cosmic structures, these enigmatic entities have left an indelible mark on the universe, serving as both beacons of the unknown and engines of cosmic transformation. Given the profound and captivating nature of black holes, one might assume that they would be relatively easy to observe and study. After all, these cosmic behemoths are some of the most massive and energetic objects in the universe, with their immense gravitational pull and intense radiation output making them stand out against the backdrop of the cosmos. But the reality is that observing and detecting black holes is an immense challenge, one that has pushed the boundaries of our scientific capabilities and required the development of increasingly sophisticated techniques and technologies. For black holes, by their very nature, are the ultimate embodiment of the unobservable, regions of space-time from which not even light can escape, rendering them invisible to our traditional means of observation. Indeed, the first theoretical prediction of the existence of black holes made by the legendary physicist John Michell in the late 18th century was met with skepticism and disbelief. It was not until the 20th century, with the groundbreaking work of Albert Einstein and the subsequent development of modern astrophysics, that the concept of black holes began to gain widespread acceptance and scientific investigation. Even then, the challenges of observing these cosmic anomalies remained daunting. For unlike other celestial objects, such as stars and galaxies, which emit copious amounts of electromagnetic radiation that can be detected by our telescopes and instruments, black holes are inherently dark and invisible. They do not emit any light of their own, and the intense gravitational fields that surround them can even bend and distort the light from nearby objects, making them difficult to discern. To overcome these challenges, astronomers and astrophysicists have had to develop increasingly sophisticated and ingenious methods of observation and detection. One of the primary techniques involves searching for the telltale signatures of black hole activity, such as the high-energy radiation and powerful jets of matter that can be produced by the accretion of material onto the black hole's event horizon. By studying the properties of this emitted radiation, scientists can infer the presence and characteristics of the black hole itself, from its mass and spin to the nature of the material it is accreting. Additionally, the distortion of light caused by the intense gravitational fields of black holes can be used to detect their presence through techniques such as gravitational lensing and the observation of the motion of stars and gas clouds in their vicinity. Perhaps one of the most groundbreaking recent developments in black hole detection has been the rise of gravitational wave astronomy, which has allowed scientists to directly observe the mergers of black holes and other compact objects through the detection of the ripples in the fabric of space-time they produce. This revolutionary new field of study has not only confirmed the existence of black holes, but has also provided unprecedented insights into their properties and behavior. Despite these remarkable advances, the challenges of observing black holes remain formidable, and the quest to understand these cosmic anomalies continues to push the boundaries of our scientific capabilities. From the development of ever more sensitive telescopes and detectors to the refinement of theoretical models and the exploration of new frontiers in physics, the study of black holes remains a crucial and captivating endeavor, one that promises to yield profound insights into the nature of the universe and the limits of human knowledge. As we delve deeper into the mysteries of black holes and confront the limits of our understanding, it becomes increasingly clear that these cosmic behemoths are not merely objects of scientific curiosity, but rather gateways to the unknown, portals that offer a glimpse into the very nature of reality and the fundamental forces that govern the universe. Indeed, the study of black holes has been a driving force behind some of the most profound and transformative developments in modern physics, from the refinement of Einstein's theory of general relativity to the exploration of the exotic realms of quantum gravity and the nature of space-time itself. As we continue to push the boundaries of our knowledge and explore the properties and behavior of black holes, we are sure to be confronted with even more profound and unsettling questions about the nature of the universe. What lies at the heart of a black hole's singularity? How do the laws of physics break down within the event horizon? Can black holes be used to access parallel universes or even travel through time? These are the types of questions that have captivated the imaginations of scientists and thinkers for generations, and as we delve deeper into the study of black holes, we are likely to uncover even more perplexing and challenging insights that will force us to rethink our most fundamental assumptions about the nature of reality. Moreover, the impact of black hole research extends far beyond the realm of pure science, as these cosmic titans have profound implications for our understanding of the universe and our place within it. The discovery of supermassive black holes at the centers of most galaxies, for example, has revolutionized our understanding of galactic structure and evolution, while the detection of gravitational waves from black hole mergers has opened up entirely new avenues of astrophysical investigation. As we look to the future of black hole research, it is clear that the path forward will be one of both challenge and opportunity. On the one hand, the sheer complexity and enigmatic nature of these cosmic anomalies will continue to push the boundaries of our scientific capabilities, requiring ever more sophisticated techniques and technologies to observe and study them. But on the other hand, the potential rewards of this endeavor are immense, as the insights we gain into the fundamental nature of black holes and the limits of our understanding of the universe have the power to transform our very conception of reality. From the exploration of the exotic realms of quantum gravity to the search for new frameworks that can reconcile the seeming contradictions between general relativity and the laws of quantum mechanics, the future of black hole research promises to be a journey of profound discovery and enlightenment. As we gaze out into the vast, endless expanse of the cosmos, it is natural for us to ponder the question of what the ultimate fate of the universe might be. Will the universe continue to expand and cool, gradually fading into a state of cold, lifeless oblivion? Or will the relentless pull of gravity eventually triumph, causing the cosmos to collapse back in on itself in a fiery, catastrophic end? These are the types of profound questions that have captivated the minds of scientists and philosophers alike as they strive to unlock the secrets of the universe's destiny. The truth is, the ultimate fate of the universe remains one of the greatest unsolved mysteries in all of science. Our current understanding of the cosmos, guided by the foundational theories of modern cosmology, provides us with a range of possible scenarios, each one offering a unique and thought-provoking vision of the universe's future. From the steady, relentless expansion predicted by the standard cosmological model to the more exotic possibilities of cyclical universes and the eventual Big Crunch, the path ahead for our cosmos remains shrouded in uncertainty, a testament to the profound complexity of the universe we inhabit. As we delve deeper into the various theories and models that seek to shed light on the future of the universe, we are confronted not only with the limitations of our scientific knowledge, but also with the profound philosophical and existential implications that accompany these cosmic speculations. For the destiny of the universe is inextricably linked to the very nature of existence itself, and the answers we uncover may well transform our most fundamental conceptions of reality and our place within it. At the heart of our current understanding of the universe's future lies the standard cosmological model, also known as the lambda CDM, lambda-cold dark matter model. This model, which has been refined and corroborated by a wealth of observational data, paints a picture of a universe that is destined to continue expanding and cooling, gradually fading into a state of increasing entropy and isolation. The key to this vision of the universe's future lies in the two primary components that are believed to make up the majority of the cosmos: dark matter and dark energy. Dark matter, the mysterious and unseen substance that accounts for the vast majority of the universe's mass, serves as the gravitational scaffolding upon which the large-scale structures of the universe are built. Dark energy, on the other hand, is a pervasive and repulsive force that is believed to be inherent to the very fabric of space-time itself, driving the accelerating expansion of the universe. According to the standard cosmological model, the interplay between these two cosmic components will shape the ultimate fate of the universe. As the universe continues to expand, the influence of dark energy will become increasingly dominant, causing the rate of expansion to accelerate and the gravitational pull of dark matter to gradually weaken. Over time, this will lead to the gradual dispersal and isolation of galaxies, as the ever-increasing distances between them make it increasingly difficult for them to interact and influence one another. Ultimately, this relentless expansion and cooling will lead to the end of the universe as we know it, as the temperature of the cosmos approaches absolute zero and the last vestiges of life and structure are extinguished. In this bleak vision of the future, known as the heat death of the universe, the cosmos will become a vast, empty, and lifeless void, a state of maximum entropy in which no further change or evolution is possible. While this scenario may seem grim and devoid of hope, it is important to recognize that the heat death of the universe is not the end of existence itself, but rather the end of the cosmos as we understand it. In this future state, the very laws of physics may be fundamentally different, and new forms of existence and reality may emerge that are beyond our current comprehension. Moreover, the timescales involved in this gradual fade into oblivion are so vast that they are nearly impossible for the human mind to fully grasp. We are talking about trillions upon trillions of years, a span of time that dwarfs the entire history of our universe since the Big Bang. And it is possible that even within this bleak and lonely future, there may be pockets of activity, unexpected phenomena, and even new forms of life and intelligence that defy our current models and predictions. While the standard cosmological model presents a rather bleak and somber vision of the universe's future, there are other theoretical possibilities that offer a more dramatic and cyclical fate for our cosmos. One of the most intriguing of these alternative scenarios is the concept of the Big Crunch, a potential reversal of the Big Bang that would see the universe eventually collapse back in on itself in a catastrophic and fiery end. The idea of the Big Crunch is rooted in the fundamental tension between the forces of gravity and dark energy that shape the large-scale structure of the universe. While dark energy is driving the accelerating expansion of the cosmos, gravity remains a powerful and ever-present force, constantly working to pull matter and energy back together. According to the Big Crunch scenario, if the gravitational pull of matter within the universe were to eventually overcome the repulsive force of dark energy, the expansion of the cosmos would begin to slow and eventually reverse. This would set in motion a process of collapse, as the universe would begin to contract back in on itself, with the vast distances between galaxies and other cosmic structures gradually shrinking. As this contraction continued, the intense gravitational forces would begin to tear apart galaxies, stars, and even the very atoms that make up the building blocks of matter. The universe would become hotter and denser, with the fabric of space-time becoming increasingly distorted and warped, until finally, the cosmos would reach a point of ultimate compression and heat, mirroring the conditions that existed at the moment of the Big Bang. At this point, the universe would reach a critical threshold known as the Big Crunch, where the laws of physics as we understand them would break down, and the very nature of reality would be transformed. Some theories suggest that this moment of cosmic reversal could lead to the creation of a new, baby universe, born from the ashes of the old, setting the stage for another cycle of expansion, structure formation, and eventual collapse. The idea of the cyclical universe, in which the cosmos repeatedly expands and contracts, is a captivating one, as it challenges our notions of the universe as a linear progression from a single beginning to an eventual end. Instead, it suggests a cosmic dance, a perpetual cycle of birth, growth, and rebirth, with the universe constantly reinventing itself and shedding the old to make way for the new. Of course, the possibility of a Big Crunch and a cyclical universe is not without its own challenges and uncertainties. The precise nature of the forces that would drive such a reversal, as well as the properties and behavior of the universe at the point of maximum compression, remain poorly understood. And the idea of a cyclic universe raises profound questions about the nature of causality, the origins of the universe, and the very meaning of existence itself. Nevertheless, the concept of the Big Crunch and the cyclical universe remains a tantalizing possibility, one that has captured the imagination of scientists and thinkers for generations. As we continue to explore the boundaries of our understanding and push the limits of our knowledge, we may well uncover new insights that shed light on this intriguing vision of the universe's destiny. Closely related to the idea of the cyclical universe and the Big Crunch is the concept of the Big Bounce, a theory that posits an even more radical and profound vision of the universe's fate. According to this model, the universe is not destined for a single linear progression from the Big Bang to an eventual heat death or Big Crunch, but rather a perpetual cycle of creation and destruction, with each cycle giving rise to a new and distinct universe. The underlying premise of the Big Bounce is that the universe, rather than collapsing back in on itself in a Big Crunch, may actually reach a point of maximum compression and density, at which point the laws of physics as we know them would break down. At this critical juncture, the very fabric of space-time would be transformed, and the universe would experience a dramatic reboot, a rebirth that would give rise to a new, distinct cosmos. This process of cyclical expansion and contraction, with each cycle potentially giving rise to a new and unique universe, is a profoundly fascinating and challenging concept to grapple with. It challenges our most fundamental notions of the nature of reality, causality, and the meaning of existence itself, as it suggests that the universe we inhabit may be just one of an endless succession of cosmic cycles, each with its own set of physical laws and properties. Moreover, the Big Bounce model raises the tantalizing possibility that the universe we observe may not be the first in this cosmic cycle, and that the very origins of our existence may be rooted in the remnants of a previous cycle. This idea, known as the multiverse hypothesis, suggests that our universe may be just one of countless others, each with its own distinct set of physical laws and properties, all of which are the product of an eternal, repeating cycle of creation and destruction. Of course, the Big Bounce and the multiverse hypothesis are not without their own set of challenges and uncertainties. The precise mechanisms that would drive such a dramatic transformation of the universe at the point of maximum compression remain poorly understood, and the very nature of the reboot process that would give rise to a new cosmos is a subject of intense scientific debate. Moreover, the implications of the Big Bounce and the multiverse model are profoundly unsettling as they challenge our most fundamental notions of causality, free will, and the very meaning of existence. If our universe is just one of an endless succession of cosmic cycles, then the very idea of a unique, singular origin for the cosmos becomes meaningless, and the concept of a linear progression from a definitive beginning to an eventual end becomes an illusion. Despite these challenges, the Big Bounce and the multiverse hypothesis remain captivating and intriguing possibilities, offering a vision of the universe's destiny that is both awe-inspiring and deeply humbling. As we continue to explore the boundaries of our understanding and push the limits of our knowledge, we may well uncover new insights that shed light on this profound and enigmatic vision of the cosmos. As we consider the various theories and models that seek to shed light on the ultimate fate of the universe, it becomes increasingly clear that the future of the cosmos remains shrouded in uncertainty. The truth is, despite the remarkable progress we have made in our scientific understanding of the universe, there are fundamental limitations to our knowledge that make it impossible to predict with absolute certainty what the future holds. At the heart of this uncertainty lies the profound complexity of the universe itself, a cosmic tapestry woven from the intricate interplay of countless physical processes, forces, and components, each of which is subject to its own set of uncertainties and unknowns. From the nature of dark matter and dark energy to the behavior of matter and energy at the most fundamental levels, there remain vast swaths of the universe that defy our current models and theories, leaving us to grapple with the tantalizing possibilities of the unknown. Moreover, the very nature of the universe's evolution and the forces that shape its destiny are subject to a level of uncertainty that can be deeply unsettling. The delicate balance between gravity and dark energy, for example, which is believed to be the driving force behind the universe's accelerating expansion, is not fully understood, and small changes in the properties of these cosmic components could have profound implications for the future of the cosmos. Similarly, the precise nature of the processes that would drive a potential big crunch or big bounce remain poorly understood, and the very limits of our current physical theories make it difficult to predict with any certainty the behavior of the universe at the extremes of its expansion or contraction. This fundamental uncertainty, this acknowledgement of the limits of our knowledge, is a humbling and profound realization that has profound implications for our understanding of the universe and our place within it. It reminds us that, for all our scientific progress and technological advancement, there are some mysteries of the cosmos that may forever elude our grasp, and that the ultimate fate of the universe may remain forever shrouded in the unknown. And yet, this uncertainty is not a cause for despair, but rather a source of inspiration and wonder. For it is in confronting the limits of our knowledge that we are driven to push the boundaries of our understanding, to explore the unknown, and to seek out new frontiers of discovery. It is this spirit of curiosity and the relentless pursuit of knowledge that has fueled the remarkable progress of science throughout human history, and it is this same spirit that will continue to guide us as we grapple with the profound mysteries of the universe's destiny. As we bring our journey through the mysteries of the cosmos to a close, it is clear that the ultimate fate of the universe remains one of the greatest unsolved puzzles in all of science. From the steady, relentless expansion predicted by the standard cosmological model, to the more exotic possibilities of cyclical universes and the eventual big crunch, the path ahead for our cosmos is shrouded in uncertainty, a testament to the profound complexity of the universe we inhabit. Yet, in the face of this uncertainty, we find ourselves confronted with a sense of wonder and awe at the sheer vastness and beauty of the cosmic tapestry that surrounds us. For the universe is not merely a collection of stars and galaxies, but a grand, ever-evolving symphony of matter, energy, and the fundamental forces that govern their interplay. Whether the universe is destined to fade slowly into the cold, dark void of maximum entropy or to undergo a dramatic reversal and rebirth, one thing is certain: the story of the cosmos is far from over. As we continue to push the boundaries of our knowledge and explore the unknown, we are sure to uncover new insights that will transform our understanding of the universe and our place within it. For the universe is not a static, predetermined entity, but rather a dynamic, ever-changing tapestry woven from the intricate dance of the fundamental forces of nature. And it is our role as curious and inquisitive beings to unravel the mysteries of this grand cosmic drama, to explore the boundaries of the unknown, and to seek out the answers that will illuminate the true nature of existence itself. So let us embrace the uncertainty of the future and let it inspire us to greater heights of discovery and understanding. Let us continue to gaze out into the night sky, to ponder the profound questions that have captivated humanity for generations, and to push the limits of our knowledge in the never-ending quest to comprehend the true nature of the universe and our place within it. For in doing so, we not only expand the frontiers of human understanding, but we also connect ourselves to the grand, cosmic narrative that has unfolded since the very beginning of time. We become a part of the endless tapestry of creation and transformation, a thread in the vast and intricate web of existence that stretches out across the boundless expanse of the universe. And who knows what wonders and mysteries await us as we continue this cosmic journey, exploring the unknown and confronting the limits of our knowledge. The future of the universe may be uncertain, but the path that lies ahead is one of endless possibility, a journey of discovery that promises to transform our understanding of the world and our very selves.
Thank you so much for watching my videos. Please subscribe to my channel. Thank you.